All right, everybody. Welcome back to another day of sponsor demos. Speaking of our sponsors, let's give them a big round of applause here and a thank you from all of us here at QHack. Thank you for all that you do. You do a lot to make this event possible. We do appreciate you. You might notice that I'm wearing a QHack 2022 shirt. You have not entered a time machine and gone back 2 years. I'm just wearing this shirt because, yeah, I like it. So there's quite a bit of things to go through. There's a laundry list of things I need to talk about. Let's go to the QHack website for a second here. So as of right now, maybe it'll take a second because traffic's pretty high. The Open Hackathon should be open at 10 a.m. Eastern, and it's not quite there yet. So this tab will be open very shortly. Make sure you go and check it out. Quite important there. There's some cool categories and lots of cool prizes up for grabs as well. So check out the prizes tabs for that. The coding challenge leaderboard will be snapshotted at 12 p.m. Eastern time as well to figure out power-ups for the Open Hackathon. I think the top 49 teams will get power-ups. There are several teams that have completed every challenge in the coding challenges. Wow, 12 already. I think yesterday was around 8. So 4 people overnight in North America completed all the coding challenges. So well done, everybody. At 12 p.m. Eastern time, so right at noon here, the leaderboard will be snapshotted and so that we can award power-ups. But the coding challenge competition does close at 5 p.m. Eastern time. So no pressure there, but that's when it closes. You can still try out the coding challenges after that, so you can still get the badges and everything like that. But the competition closes. So again, you can submit to the coding challenge platform after the competition ends at 5 today. Yeah, so keep working on them if you haven't even solved them already yet. There's tons of badges up for grabs as well. That'll be really fun. They'll be on your Penny Lane profile. Right, let's go to the schedule for today. So if you did want to see the schedule on the website, I'll have it up on the stream here in a second. But you just go to the online events tab and click on streaming sessions, scroll down a bit, and this is the schedule for today. Quite a bit going on. We have a talk from Leonardo coming up very quickly here. And I think we'll just get into that, actually. So let's get right into today's talk. We have Leonardo joining us from Entropica. And Leonardo, I do actually want to just read your bio off because I thought it was kind of funny. So I'm going to read it all in its entirety. Leonardo graduated as a theoretical physicist from the University of Edinburgh, earned himself a PhD in quantum information from Telecom Paris Tech, and successfully learned how to code and be a programmer. He's pretty pleased with how things have turned out so far. So he's decided to become a proper quantum scientist, and now he enjoys working at Entropica while busking in Singapore's tropical climate. In his free time, he likes to cook, walk his dog, and train for the next marathon. This is my favorite part. Oh, he also apparently likes to write in the third person. So, Leonardo, it's lovely to have you with us. How are you doing today?
I'm doing great. Thank you. Thank you for having me here. And yeah, I'm glad you liked my bio. We all like to write about ourselves in third person, it seems. So
yeah. All right. Well, you're going to talk to us about the need for a new software stack for quantum error correction. So the floor is yours.
All right. Thank you. Thank you, everyone. So yeah, let's get into it. So you already introduced me. So a couple of things have changed since then. So I became the head of R&D at Entropica Labs. That did not happen in between me sending the bio to the QHack people and the presentation. But that's what's one of the new things in my life. Entropica Labs is a company, is a startup in Singapore, trying to make quantum computers useful, like many other startups out there. You may have interacted with me already because I'm a developer and maintainer of OpenQOA. It's an open source package sponsored by Entropica to solve the quantum approximate optimization algorithm. And indeed, if you participated in QHack in the last couple of years, you might have heard a few talks from us on that topic. But today, I'm here to talk about something slightly different. So today I will be talking about the role of software. It's a very packed day, so on purpose, I try to make this presentation lighthearted and simple. And I'm wondering, maybe even a bit too simple. That's how I see software. You have the user on one hand, and you have the quantum computers on the other one. And software is the thing that bridges that gap, is what takes you there. I know this is trivial, but my point is trying to argue that it's perhaps not as trivial as it sounds at first. So today, I argue, we know the stack fairly well. So we have a well ironed out stack to connect and use quantum computers. My claim is that quantum error correction will change things. It will add an extra layer of complexity to this stack. And I think for everyone interested in quantum computing in general, this is something they should know. Maybe you will not end up using these things directly, totally possible and totally fair, but I think it's worth looking into that. And anyone in the industry out there will probably have to do so in the next years. So let's get started. What's the flow of a quantum algorithm today, at least? So you start wherever really you want to start from. Could be a book, good old Nilsson and Chuang. It could be a paper on the archive. It could be Penny Lane. It could be OpenQA, Qiskit, your favorite library. Wherever you start from, you end up having an ideal quantum algorithm. And once you have this ideal quantum algorithm that usually you write out as a circuit, but it could even be in a different formalism. It could be measurement based or anything you want. Then you use software to get an executable quantum program. This is like the flow, really, like how we tend to think about this concept. And of course, eventually you will send this off to a quantum computer. So executable here just means that it's something that if you send to a quantum computer, the quantum computer will know how to run that particular program. So far, I think so good. Nothing too revolutionary here. Ideal quantum algorithms. What are those exactly? So the idea is that each qubit in your ideal quantum algorithm is treated as a perfect qubit. So what I mean by that is that your ideal qubits are in a one-to-one map to the physical qubits of your hardware device. This will change later on through the talk. And if it sounds a little bit not very clear right now, or a bit confusing, I hope it will be clear as we go through. So it's a very simple example. In this situation, I have a classical quantum circuit over here, my wires and my gates and whatnot. And all I'm saying is that when I think about this algorithm, I hope you can see my mouse, the first wire goes to one physical qubit on the device. In this case, is the IonQ harmony device. Likewise, number 2, and so on and so forth. And of course, I can map them anywhere I want within this hardware. But the important thing is that each qubit in my ideal quantum circuit is, in some sense, perfect. Is ideal. It represents everything I would like to have from a qubit. So in some sense, what I'm saying here is that we kind of fundamentally assuming there is no noise or errors. And this is perfectly fine. If I want to design a new algorithm, this is a perfectly valid way to look at the quantum algorithm. But it's nonetheless a strong assumption we are making there. And I will show you as we go through this presentation how quantum error correction will sort of challenge this idea of a one-to-one map. And when I said there is no noise or errors, again, in the spirit of making the presentation a bit lighter, I tried to ask ChatGPT to come up with a few pictures to illustrate, and indeed, it reminded me of when you try to model something in the early physics courses at university, and you say, well, okay, I have a unicorn, but fundamentally a unicorn will just be a sphere, and there is no air friction and it's vacuum, so I'm just gonna have a sphere rolling down some slope, and that will be my unicorn. No need to actually sort of go into the details of how the unicorn has 4 legs or whatever. So we covered the ideal quantum algorithms. The next step is the executable program part. How do we obtain executable programs with software? Again, I asked ChatGPT to draw a presentation ready image of a quantum circuit based on Qiskit diagrams. That's what he came up with. I thought it was funny enough that I would leave it. So that's my ideal quantum circuit. Any algorithm, could be Grover, could be Shor's algorithm, anything really. And the idea is I have some hardware and I would like to run this algorithm using that particular hardware. In this case, I just picked the IBM Brisbane topology hardware. And the claim is that today we know the steps pretty well. So first of all, you will have to sort of translate your ideal quantum algorithm using only native gates. So not using gates that are not supported by the machine. You'll need to select which qubits you want to use. I have 128 qubits here. Maybe I need all of them. Maybe I need a subset. Which ones I need to map my ideal quantum, my ideal qubits in the circuit to the hardware. I may need to do some routing, some pulse control, schedules. The list is long. And of course, the list changes if I deal with ion traps or neutral atoms or photonic devices. But at its core, these steps are relatively well known. They may be difficult, but we kind of know them by now. This is all amazing, right? Having worked on NIST devices for the past 4 or 5 years, actively trying to run computation on them, I surely relate to the next meme, and I guess many of you do as well. Just leave it here for a second. You know, every time you try to run something on a quantum computer is the same. It turns out that you always hope the results will be better than the rubbish at times you get back. And of course, what happens is that there are a lot of noise. There's a lot of errors, there's noise, and things never quite work the way you expect them to work. That's fine, it's part of the game, but we need to do something about it. So there are two strategies we can employ: error correction and error mitigation. Now, first of all, I want to say these are two different things. So my goal today is not to claim, oh, error correction is so much better than error mitigation, or the other way around. They're just different things, different ways of thinking about how to deal with problems and how to solve certain problems. So error correction, a technique to correct errors by embedding your ideal quantum program within some quantum error correction code. Now, this will be a bit more clear later on what it means, but fundamentally, the goal of error correction is to correct errors. You want to know what error has occurred on your device, in your computation, and you want to do something to fix that error. On the error mitigation side of things, on the other hand, we have a set of techniques that try to improve the fidelity of the operations you're performing on your quantum device. And this could be the operation themselves or the measurements when there is some noise. Indeed, you can try to apply error mitigation techniques to an error correction code. So the two things are not exactly opposed one to the other, but their goals are slightly different, and that makes a big difference in my opinion. At Entropica Labs, we don't really feel we have a choice. We have decided that we want to focus on quantum error correction. And that's what I will talk about after. I also want to point out that there's a lot of really good companies, some of which we'll also talk today, the later presentation, that focus on bits and pieces of error mitigations, and they're doing a great job as well, trying to improve what you can do today with quantum processors. So it's really not a fight between the two things. Now, what's the simplest error correction code? Now, the question is, I want to impress someone. So somebody's coming over for dinner and I want to bake a cake. I want to make sure that that will be a success. What can I do? What are my chances? What are my options out there? Well, one thing that I can do is I'll just bake the same cake 5 times and pick the best one. Now, that's a very simple sort of error correction algorithm, if you want, which is based on repeating the same operation over a period of time. Of course, it will take longer and I will need to spend more money buying the ingredients, but it sort of tries to help me making sure that that at least one cake will be good and I'll be satisfied with. Now, quantum mechanically, it turns out we can't do that. The reason why we cannot do that is the no-cloning theorem. The no-cloning theorem fundamentally tells you that if I have an unknown quantum state, I cannot make arbitrary copies of it. I can make a copy of it, but I delete the original one. Which means that this kind of strategy is just not going to work. Now, we can do something else. What we can do is we can use entanglement. So I took this circuit, which represents a very simple, intuitive quantum error correction code by Staines. Nice notes on error correction. The link is down there. What's happening here is that I have a state, phi, at the beginning, and I have some noise that will happen over time. And what I do is that I encode this single qubit into a system of 3 qubits. This is the original crucial step that sets me apart from the ideal quantum circuit. Rather than considering just one ideal qubit, one physical qubit, in this particular example, I'm going 1 to 3. What happens then is the noise arrives, and then I have a strategy by adding 2 extra qubits and performing some operations to actually correct for the potential noise that has arrived. And then I decouple the information, so I go back to just one system, and then I'm good to go. So what are we doing here is that we're using entanglement to create some redundancy in my information, and this is really the core of error correction, quantum error correction. So what's the flow of a quantum error corrected algorithm? Well, start from the same as before. I have my input and I get an ideal quantum algorithm. Once I have that, I will embed this into a quantum error correction code. I will perform some checks because I want to make sure that this embedding has worked out correctly. So I need to check for error correction and I need to check for fault tolerance. Fault tolerance, I'm just throwing a bit more stuff at you. It basically, in a nutshell, simplifying things, it's a way to look. It's a way to make sure that you're not just correcting errors, but you also prevent errors from spreading out of proportions. And once you've done this, you obtain an executable and fault-tolerant quantum program. So my claim is that we need a new software stack to get executable and fault-tolerant quantum programs. And this is a big deal, and it's changing a lot of the way that we think about just software and quantum computations. So the fault-tolerant stack. The full list of steps you need to perform if you want to make sure that your computation is fault tolerant is not just long, it's partially not quite fully worked out. We are still at the beginning. A lot of people have different ideas, different plans, but what I can tell you is that it's long and it's complicated. I've picked here just one simple example just to motivate this presentation, if you want, and part of our work at Entropica. So what we want to check is the validity of the syndrome extraction circuit. Now, at the moment, it's a mouthful, so let me break this down. Same circuit as before, exactly the same thing. This part here is the syndrome extraction circuit. So what have we done? Single qubit that encodes my state that I want to preserve. I encode it into a 3-qubit system. And then what I do here is that I add 2 more qubits. I perform a bunch of C-nots, and then I perform some measurements. Now, what happens when I perform the measurements? I get a bit string. So if I get 0, 0, I know that I shouldn't do anything. If I do 0, 1, it means that I need to do an X correction on my 3rd qubit here. And if I get 1, 0, it will be an X correction here on the 2nd qubit. And if I get 1, 1 in my outcomes, an X correction here. So in all of these cases, what I'm doing is that I know how to correct for something. And syndrome, if you look at the dictionary definition of it, is exactly a group of symptoms which consistently occur together. So I look at the symptoms and then I know what I need to do. Checking the syndrome extraction. What does that mean? Let's look at a real example. Here, that's a surface code. It's a complex beast made of many qubits. Each dot, it's a qubit. White dots are data qubits. Black dots will be the ancilla qubits, these extra qubits I put in order for the algorithm, the quantum error correction algorithm to work. Each one of these stars, the yellow and sort of green bluish ones, is composed by a quantum circuit. And now my task is, well, now I want to run this on a real device. How am I going to do that? Now, if I try to do this, it becomes very complicated and very quickly. And I also really want to make sure that my conditions, the error correction conditions and the fault tolerant conditions are satisfied. This is difficult. I can't do this by hand because the problems get very quickly too large. I need software to solve this problem. And solving this type of problems will be fundamental as we go through in our sort of quest of making quantum computers useful. So we are in search of this fault tolerance stack because we need software to ensure our ideal quantum algorithms are executable and fault tolerant. And to conclude, this is not just about compilation. I made the example sort of going from a circuit to some hardware and arguing that, well, it's difficult to put stuff on a superconducting device. It's not just about that. It's really about optimizing fault-tolerant circuits. It's not sometimes just enough to come up with a naive fault-tolerant circuit. Sometimes you need to make that work and work nicely. And that's not going to be a trivial task. A lot of software is going to be needed to make that possible. And what I said also applies to all quantum computing platforms. It applies to ion traps, photonics devices, neutral atoms platforms, and you name it. it's not just a feature of superconducting qubits. I just used that as an example. With this, I think my time is probably almost over. So I thank you for your time and your attention. I'm happy to take some questions, and thank you.
Thank you, Leonardo. Really appreciate that. Really liked your talk there. We have a couple of questions, but for those of you who still have questions for Leonardo, he will be on the Discord. So go to the Discord afterwards if you want to bother Leonardo more. Okay, a couple of questions here. We've got one from Catalina. Right, Entropica has a quantum research engineer position on our job board. So you can go check that out if you want to. Our job board's on QHack.ai. So she's just asking, Leonardo, do you have any tips for people applying to the quantum research engineer position?
Be curious. So in general, one of the features that we look for more sort of junior position is curiosity, apart of course from the ability of knowing quantum computing and everything. I know it sounds trivial, but if you want to work for a startup the size of Entropica, we're about 15 people at the moment. Hiring is always complicated. So if you want to apply to such a startup, you really need to come across as motivated. So as a general suggestion, I will say that. The rest, like the details of like your ability to use Python or whatever else, those are all things that can be probably fixed over time. But the motivation and sort of that will of working for a startup compared to a bigger corporation is definitely something that we value a lot. Yeah.
Right, there you go. Okay, so that's all we have time for, Leonardo. Thank you so much. Everybody hop on the Discord if you want to chat with Leonardo some more. But for now, Leonardo will say goodbye. And
right.
Yeah, chat
Thank
soon.
You very much.
Have a great rest of your day.
You too. Bye-bye.
All right, bye. Okay, everybody. We got some more stuff coming up. Right after Leonardo's talk, we have talks from Haiqu. We have two people joining us from Haiqu to talk about middleware software stacks. So that'll be fun. So definitely stick around for that. We'll be back in about 10 minutes. See you soon. All right, everybody. Sorry about that. Just a little bit of technical difficulty on my end, just getting everything to look very pretty for everybody here. So up next, we have Maciej and Yuriy from Haiqu giving us a talk. So let me just read off quickly what Maciej and Yuriy do. Maciej is a principal scientist at Haiqu. Prior to joining Haiqu, he worked on applications of machine learning and information theory in statistical physics and was a postdoc at ETH. Yuriy is the lead engineer at Haiqu when he focuses on merging quantum computing with AI. Before Haiqu, he was a startup founder and a senior engineer with several companies working on AI and computer vision. So Yuriy, Maciej, welcome to both of you. It's great to have you here. Yeah, excited to hear your talk. The floor is yours whenever you see fit.
Lovely. Thank you, Isaac, for the introduction. Yeah, hello. Welcome, everyone. My name is Maciej Koch-Janusz. I'm the principal scientist at Haiqu. And today I wanted to tell you just a little bit about the difficulty of running quantum algorithms on the actual quantum hardware, and also how Haiqu is developing software tools to make this possible. One of these tools you'll be able to preview and hopefully also even deploy during the hackathon. So Haiqu is a quantum computing software startup focused specifically on development of quantum middleware to help unlocking the potential and practical utility of quantum computing in various applications, such as in pharma, logistics, finance, and many others. The promise of such applications is, of course, the main driver of any investment in quantum computing. So in this short presentation, I will cover the importance of quantum middleware in the quantum computing stack, and I will showcase some of the improvements in quantum circuit execution on near-term devices, which may be achieved using Haiqu's technology. We'll also preview Rivet, the quantum machine learning tailored quantum compiler from Haiqu. And finally, I will very briefly introduce the team behind Haiqu, and I will mention some collaboration and internship opportunities for those of you who may be interested. So the roadblocks to the practical utility of quantum computing are in fact twofold. The first and the most fundamental one is the noise. Quantum hardware suffers from numerous sources of noise, all of which ultimately manifest themselves as errors in the final computation. So the rundown includes energy relaxation processes of T1 noise, dephasing, or T2, various coherent errors, such as, for instance, systematic gate over or under rotation, more complex correlated errors, such as crosstalk, as well as errors both in the initial state preparation and also in the final result measurement readout. All of these, if left unchecked, will conspire to render most any computation effectively useless, garbage noise. The other roadblock has to do with the limited scale of the currently available devices. The most obvious number to think about is the physical qubit count, but equally important is the device connectivity, its gate set, and the measurement rate. So different architectures may vary in these respects by orders of magnitude, and actually a fair comparison between them is not entirely trivial. While the focus is often on the qubit count, it is really important to note that the number of physical qubits has, in fact, been growing much faster than the effective number of practically usable qubits, as measured, for example, by the quantum volume metric. As you see in the table on the right, some of the quantum devices with physical qubit counts in hundreds have rather small effective qubit numbers. That's the logarithm of the quantum volume metric. So what is this quantum volume? Well, quantum volume is a holistic measure of performance of the full quantum computing system, crucially including both its hardware and software components. On a more technical level, the test is statistical, measuring whether the likely measurement outcomes as defined by the idealized circuit you actually want to run are in fact still likely to be obtained when performed on the actual QPU system. And so the largest square-shaped random quantum circuit, which can be performed on the QPU and passes this test, defines the quantum volume of the device. In other words, it tells you how many high-quality controllable qubits on which you can perform operations and execute gates you really have effectively. And as you see from the table, that number is almost always an order of magnitude lower than the physical qubit count. Note also that the quantum volume test circuits are defined using idealized gate sets and linear topology. Therefore, before the execution, they have to be transpiled to the actual device gate set and the actual topology. And the properties of the architecture, such as qubit connectivity, as well as the quality of the compiling and other software involved in this compiling and execution process, will crucially influence the outcome. So there are, in fact, a number of different ways in which the quantum volume can be improved by software rather than hardware-based methods. The compilation process is an obvious one, as better transpiling will result in shorter depth device executable circuits, which are therefore less affected by the noise. Similarly, qubit mapping and routing may be also crucially important because it allows you to take advantage of the best possible subset of the physical qubits, which very often differ in quality, especially, for example, for superconducting architectures. So a key component in some of the impressive recent results on near-term device utility, such as the IBM's Quantum Volume 64 demonstration paper or the many-body localization paper, has been also the use of software-based quantum error mitigation techniques, such as zero-noise extrapolation or probabilistic error cancellation. But in fact, there are many others available, and they come at a different computational cost. And so the development of such software components is the province of the so-called quantum middleware. So at the most basic level, we tend to think of quantum computing technology stack focusing either on its top part, that is the theoretical algorithm primitives, Grover's algorithm, Shor's, QFT, and so forth, and also their applications to the specific domains, the user-defined problems, or on the contrary, we focus on the very lowest hardware level, that is the actual QPU and its control software and control electronics. Quantum middleware is the slightly less glamorous, but nevertheless entirely crucial intermediate component linking these two parts together, and thus, in fact, enabling any potential future commercial utility of quantum computing. Now, the two fundamental ways in which this software layer of quantum middleware can improve the performance of the whole quantum computing stack are through, one, reducing the impact of the hardware noise, to which I already alluded before, and two, through increasing the effective scale of possible quantum computations. That also includes the classical component. So many of the current demonstrations in the scientific literature are focused on small research level problems of purely scientific interest. In deployment to future practical applications, the computing infrastructure will have to contend with similar problems as, for example, providers of cloud-based computing resources for classical machine learning have to contend with today. So developing appropriate scalable solutions is also the province of quantum middleware. So with this in mind, Haiqu focuses its efforts on the development of the quantum middleware as the key enabler of practical utility of quantum devices. The Haiqu system comprises a set of components focused individually on each aspect of the quantum computing workflow from the perspective of the user, and is designed to streamline it. So first, the analysis tools to provide the user with the information about the properties of their circuits, particularly with respect to the intended hardware on which they are to be run. So this allows the user to anticipate the potential difficulty, achievable quality, and also to estimate the currently, unfortunately, very substantial dollar cost of the actual execution on hardware. Then there is custom compilation packages allowing flexible use of our in-house, third-party, and also open source components to tailor the best possible circuit for the actual execution. There is the error mitigation, which is a suite of our custom and also open source error mitigation methods, such as, for example, the already mentioned zero-noise extrapolation and a bunch of others. Finally, there is the circuit execution component. Haiqu has proprietary strategies of executing the compiled circuit to minimize the impact of the hardware noise, and therefore to maximize the capabilities of the existing devices such as they are today. So let me now focus specifically on the optimized execution subsystem and showcase some of its capabilities. So to benchmark this component, we performed noisy simulations on fake devices of different vendors, both of IBM and others. So here I'm showing you the results of the quantum volume test that I already discussed before. So it's a quantum volume test execution on a simulated 27-qubit device, 27-qubit IBM Kolkata device, which is available in Qiskit as fake Kolkata, for which, as a baseline using standard best Qiskit level 3 compiler settings, we measure the quantum volume of 32, that is 2 to the 5. That is, this device is able to accurately execute a random circuit of up to 5-qubit width and 5 layers depth. So this quantum volume result is consistent with independent estimates that are available in literature, and this is basically the level which is achievable by a typical advanced user. So the quantum volume is depicted in the plot, where on the x-axis we have the circuit depth, and on the y circuit width. And the area where the quantum volume statistical test is passed is denoted by the pale blue shading. As you see, with Haiqu's optimized execution subsystem, the quantum volume statistical test is passed by the very same simulated devices in a much larger area, corresponding to the quantum volume of 128, that is 2 to the 7, and that's shown here in the darker blue. And I want to emphasize here that the gain is, of course, with respect to that chosen baseline, and that in principle, our tools can also be combined with additional optimization to provide even further increase in quantum volume. Well, this increase in quantum volume obviously automatically entails the ability to execute basically slightly wider circuit and slightly deeper too. But crucially, as you see in the plot, when we relax the constraint of running only square-shaped circuits, as in the quantum volume test definition, we observe that our execution strategy allows to accurately execute significantly deeper circuit than the nominal quantum volume value might suggest for the same circuit width, which, of course, that ability to run much longer circuits is very important in practice. Now, quantum volume circuits are a great test of devices and of the software system, but precisely because they're designed as a challenging benchmark, their complexity is actually beyond typical sparse application-derived circuit. And as an application-oriented developer or a practical user, you may therefore be interested in the empirical performance of the system on actual use case-derived circuits. So we have therefore performed a number of such benchmarks for different algorithm families to test well the optimized execution strategy. So here I'm showing to you the results of running so-called volumetric tests on a key algorithmic subroutine of amplitude estimation. So the results are plotted similarly to the quantum volume results from the slide before. And in fact, the quantum volume, both of the original and Haiqu improved one are shown also. On top of that, we overlaid the fidelity of execution of amplitude estimation circuit with an increasing number of qubits. And as you see from the bottom plot, for the original execution, the 5-qubit amplitude estimation circuit, which lies already outside the quantum volume rectangle, so the circuit is already deeper than 5 layers. It has a fidelity of below 40%, and above that, above more than 5 qubits, the result is essentially noise. In contrast, with Haiqu's optimized execution, 5 and 6 qubits amplitude estimation circuits are executed with high fidelity, despite being well outside the quantum volume ranges, and that only drops to 40% for 7 qubits. And we, of course, have similar results for other important application algorithm families. Now, I've shown you some of the Haiqu technology and how it can improve the quality of the results obtained on the noisy processors. Obviously, there's a lot of research that's going into developing these techniques. But in tackling the more fundamental problems, we also continuously run into more practical daily challenges. And to overcome these, Haiqu is developing some in-house solutions and utility software tools. And we've realized that some of these may also be of use to the broader community. And we have therefore decided to make some of them also publicly available. And one of such tools, the first one actually, that we release is an open source quantum machine learning compiler, which we call Rivet. And Yuriy, Pryyma, our fantastic lead software engineer, will give you a preview of that. I'll shortly give the floor to Yuriy, but I'll come back at the end of the presentation. Yuriy, the floor is yours.
Thank you, Maciej. Hi, everyone. I'm Yuriy, lead engineer at Haiqu, and today I'm delighted to talk about transpilation and how you could speed it up by a few order of magnitudes. I'm coming from AI background and worked mostly on computer vision and reinforcement learning and building software infrastructure around them. So from my experience in AI, I have seen how good software tools like PyTorch and TensorFlow is important to build a community. And I feel the same for quantum, as AI in applications and AI in quantum pipelines, as well as software, is important to move a field forward. So as I joined Haiqu about a year ago, and coming from different domain, I was onboarding to Quantum. And one of my first tasks was to play with and understand how classical shadow works. Just to onboard everyone else, what the goal of classical shadow is to reconstruct a quantum state of your system. So how you could do it? First, you need to have a quantum system you want to measure. Then you could apply, you need to apply random unitary to change the basis of your system. And then you want to measure in this basis. And you just need to do a few thousands of this measurement to get the result. Then you could follow the protocol of classical shadow to do to make a reconstruction, and in the end, you will have your final reconstructed state. So don't be afraid. We're not going to dive more deeper into this protocol. It will just be an example that we will follow through our slides. So let's just focus on how you could implement applying this random unitary to a quantum system, and then doing measurements in some quantum framework like Qiskit. So at first step, we need to create a quantum state. You could easily do this using the Qiskit quantum circuit, and you just add some random gates that you want for our test case. Then you decide on a random Pauli basis you want to measure in, and just iterate through all of your qubits and add corresponding gates on top, and measure the qubits that you need. Then, if you want to run the circuit on a real hardware and not only on some noiseless simulator, you need to transpile it. And I will talk more about this a bit later. But when you already have transpiled circuit, you could run it on hardware and have the result. And remember, we need to do many more of this transpilation different bases and running to have the final result. I implemented this procedure on my machine, and it worked very slowly. So being engineer at heart, I got annoyed and decided to debug how to solve this problem, and tried to benchmark different parts of system. So what I found out is actually transpilation time taking so much. Just like look on the plot, and here you could see the total transpilation time for different qubit cases. And for example, for 8 qubit, you need to have a few thousand of circuit executions, meaning a few thousand of circuit transpilations. And considering a transpilation could be 1 or 2 seconds, it's a few hours of just transpiling a circuit, and not only including the actually running the circuit on the hardware. So that's clearly not the quantum future we all expect. So it got me thinking how we could solve that problem. So let's just take a look at our circuit. We have our state preparation circuit, which was very shallow, just with few gates. And also we have our random unitary circuit added on top, and this also was very shallow. But in practice, that's not the case. Usually, the state preparation circuit is very huge, consisted of a few thousand of gates. And this random unitary is as small as I showed in an example. So it got me an idea. Why not just to transpile the circuit before and then add measurements in the end? So how it will look like? We will have the same state preparation as before. Then we do a transpilation of this big state preparation circuit only once before our procedure. We cache this result. And then for each of our measurements that we want to add on top, we select, as before, a random basis, go through our qubits, add the gates on top of our already transpiled circuit, and measure the qubits. And then we expect it to run on hardware. So what's the idea? Now, because we are not transpiling circuit for each of the random unitary and doing it only once, we should save a lot of time. But sorry to disappoint you, this will not work. And to understand why it will not work, we need to know more about transpilation. So what's the goal of transpilation? On one side, you have a high-level circuit which consists of complex operations, like a QFT, multi-qubit gates, or even some random unitaries applied to a circuit. And on the other hand, you have a complex quantum hardware. And maybe not all of the gates are supported on this hardware. Maybe it has specific topology and not all the qubits are connected. Or you're not aware of the noise level of different qubits, and you need to really know to be able to run on the hardware. And so transpilers try to solve this problem. It converts this high-level circuit that you have to a low-level circuit that could run on hardware. It does so by unrolling these high-level operations to the gates that support on the device, by adding conditional swap gates, which allow you to connect qubits that are not connected in a topology, and additionally do optimization to decrease the number of gates of your circuit to make it smaller and so accumulate less noise. And now, as we know more about transpilation, we may understand why our naive approach of solving our problem didn't work. First of all, you cannot just add any gate to your circuit expect it to work on the hardware. Maybe this gate is not supported on the device. Also, because transpiler adds swap gates, the qubits are located in different places on your physical qubits. And you really should know at what qubits you should put your measurements and add your gates. And also, this is not actually very case for our application, just because we're adding only single qubit gates. But when you want, in general case, add multi-qubit gates, you should also be aware of the topology of a device. So it didn't solve our problem. And why there is no simple solution for our problem? I think it's because the current transpilation procedure following a philosophy of transpile and forget, meaning that user has his high-level circuit that he wants to run on hardware, and for this he will use some quantum library like penny lane or Qiskit. And as we already know, to run a circuit on hardware, you have to do a transpilation step. But usually in these frameworks, this transpilation step is omitted or hidden from user, and he could be not even aware that it's happening. On other case, as we showed in an example right now, for classical shadow, user should be clearly aware of transpilation and follow the philosophy of like transpile and reiterate, meaning when user has his original quantum circuit, he may want to transpile it once, then add some additional gates that he needs, transpile it second times, add maybe noise mitigation, transpile it finally, and only in the end run it on hardware. And in this case, transpilation is clearly visible for a user, and user reiterates on iteration results and adds his own things. So we see that this is not only the problem for classical shadow, but for many more applications, like in quantum algorithms, when you want to combine different subroutines, for example, QFT or Grover steps, or you want to do tomography. Also, it's very big problem in quantum machine learning. Just imagine you want to do layer-wise training, and if you're familiar from AI domain, you may want to understand how much layers do you need for your virtual circuit. And for this, you need to combine and stitch layers. And this is exactly the problem that we have with classical shadow, but actually much more complicated because variational layers actually have 2 qubit gates. Also, you may want to have a modular quantum neural network, which consists of different parts, and want to combine in runtime. Also, you may want to have a different data encoding that go to the same variational model, and you want to switch it very fast in your execution. Also, that's the case of noise mitigation. For example, probabilistic error canceling, a dynamical decoupling. When you apply them, you add additional gates, and you really want to make sure these gates are not optimized out from a transpiler. And if you also know some other problems, feel free to contact us, and we would like to talk about them. So as we at Haiqu have been solving these problems, we developed our own internal transpiler, and we think it will be useful for the community. And we are happy to announce that we are releasing our open source transpiler called Rivet. And his main motto is get bigger control over transpilation. So what's Rivet? Rivet is open source transpiler which provides Qiskit-like API for transpilation and builds on top other open source transpiler. And the whole idea is to give user a modular approach to build his transpilation. So let's just go over some of its APIs to learn more about. First set of APIs that Rivet support is location API. We want to give user ability to control which part of circuit he wants to transpile and when. For this, we have a transpile right, transpile left API, and other functions. Why would you want to use them? Let's just come back to our previous example of classical shadow. We have a circuit that consists of 2 parts. One of them is a big state preparation circuit, and one other is a random unitary that we want to add on top. And that's exactly case for location APIs. We really want to control location of the circuits we want to transpile. Now, let's see example how we could use transpile right to solve our previous problem with classical shadow. First, we have the same state preparation as we was before. Then we do transpile a big state preparation circuit once, as we did in our naive approach. Then what's different, we create a separate measurement circuit consisted of our random Pauli basis and add gates as we want. Then we use this new function called transpilerite. And transpilerite has two arguments. One argument is transpile circuit that you have on your left part. And then on next argument is not transpile circuit that you have on the right. Now you could use this function and it will return you merge these two circuits that are valid and transpiled, and you could run on hardware. Why this is very important? Because in this case, we are only transpiling these very small unitaries, random unitaries that we added on top, and not transpile our whole circuit. Now, as we have the saving, we could run benchmark one more time, and we see that our basic transpilation took so long, and we decrease a time from a few hours to just a few seconds, just only doing the transpilation. So let's just move to our debug API. So as our motto of a transpiler was to give user bigger control over transpilation, user should be aware of transpilation at first place. So for this, we have a transpile and debug function. It will not only transpile the circuit, but also return you a list of all detailed information of transpilation, like what's transpilation passes, how much time does it take, and how did it change your circuit in terms of used qubits and used gate. Now you could make more informed decision about your transpilation. The other set of APIs is related to constraint API. And we want user to be able to control different properties of transpilation and prioritize some of them over the others. For this, you could use a transpile and compress function, which I will talk a bit right now. And why would you want to do this? Imagine a case when you have a 9-qubit circuit, and you want to run it on some hardware or on some noisy simulator. First, we need to transpile it. And what could happen is that during the transpilation, your transpiler adds additional ancilla qubits. Why would transpiler do this? Maybe he will want to decrease the depth of his circuit, and he uses just additional qubits to bridge the gap of connectivity in your circuit. This is cool. It saves you depth, but you pay the price of additional qubits. And you may really don't want to have them. Why? You may know that on this hardware, using the ancilla qubits is actually not welcomed. Or if you want to run your circuit on noisy dense matrix simulator, it's really important to control how much qubits you really have in your circuit. So let's just see the benchmark of running 9-qubit and 10-qubit circuit on noisy simulator. So 9-qubit circuit will take, for example, a few seconds to run. But 10-qubit circuit on some noisy density matrix simulator could take more than 10 seconds to run. And just imagine you want to run a QML job, which consists of 1,000 evaluations. So on 9-qubit circuit, and just running will take 25 minutes, but when 10-qubit circuit, it will be 200 minutes. So that's why important to say the transpiler, how much ancilla qubits and additional qubits you want to use, and that's exactly a function of transpile and compress. Now we could move to the last set of our APIs. It's called modify API, and we want to give you the ability to not only constrain API, but also change different parts of API and replace with others that you want. For this, you could use our stacks. So right now we have this available stacks. It's other open source transpiler like Qiskit, PyTicket, BQSKit with QFactor and QSearch. And we want user to give more power to use the best features of this transpiler. So why would you need to do this? Imagine you have your quantum circuit, and this circuit consists of two parts. One part is some sparse in terms of gate circuit, and other part is very dense circuit. And you may know that, for example, for this sparse circuit, synthesis optimization will do the best. Sorry if you don't know what is it, but it's kind of one of the ways to optimize your circuit. So, and you may want to use a QFactor to do this optimization. But how would you do it normally? You just have to run the synthesis optimization on your whole circuit. But you know that this big part is actually much harder, and there is no point to make running synthesis on it. So now, with combining location API and combining our stacks API, you could solve this problem. You just split the circuit in two parts, and you transpile this dense part with default transpiler, which works pretty fast. And then you transpile the other part with synthesis optimization, and it has a good quality result. And then using our location API, you can combine them together. So what you will have in the end, you will have better performance and shorter circuit, and also you will save time on transpilation. So let's just wrap up what we go through. First is that transpilation is a very important step in your quantum pipeline. Second is that future application will require more complex transpilation strategies. And we show that Rivet is bigger control over transpilation, and also it will enable this future application and optimize performance. So we are happy to open source our transpiler, and we know that hackathon is happening right now. And if you feel that some of the problems that you face could be solved with Rivet, I encourage you to go to our GitHub and go to the examples. They are in more detail, describe the API and how it works. And also, if you have some questions, please ping us on Discord, open the issue on GitHub, and contact us on email or me on LinkedIn. And also, if you're coming from industry and facing the same problem as we do and want to collaborate, we are very happy to work together. And also, please contact us on our emails. So thank you all. I will pass my word and stage to Maciej.
Yeah, thanks a lot, Yuriy. So yeah, as we have shown you, Haiqu is focused on the fundamentals of quantum circuit execution, but we're also actively developing both methods and software toolboxes to aid various practical problems that we encounter. So we are therefore extremely happy to be able to be here at QHack and to interact with the vibrant community of quantum software enthusiasts gathered here in Toronto. And even more so as Haiqu has in fact originated in Toronto, where the two founders, Richard Givan and Mikhail Maximenko, met in the Creative Destruction Lab Incubator. Now, over the span of a short year, Haiqu has grown from the founding team to a globally distributed team of almost 20 researchers and software engineers. We have a strong presence in both North America and the EU and UK. We are always happy to work with dedicated developers and also researchers. And we have a research internship program to which I encourage you to apply. So you can find the details and the contacts under the links provided in the final slide. And with that, I thank you for your attention, and I wish you a successful and most importantly, exciting hackathon. And that's it. Thank you very much.
All right, Maciej and Yuriy, thank you so much. I'll leave this slide up for a bit in case people want to go to Haiqu's website and see anything else here. Thanks so much. That was really interesting. Had some good questions in the chat, so we might as well just get right to those. We have Gloku42 on our Twitch channel asking, I think earlier in your presentation, Maciej, you were showing some results and they were wondering if there's a paper that you guys published with any results.
No, so the results are not available in the form of a paper or an ICA publication.
Okay.
We are happy to share the results in the form of a white paper with interested parties. But I have to be fairly honest here that we're currently keeping it to sort of collaborations
Sure.
with potential partners. So we're not disclosing the further details in the form of publication. But of course, one will be forthcoming.
Sure. Okay. Thank you. Another question from Dentucky Kirby on our Twitch. I always get confused. What's the difference between transpilation and compilation?
I could answer.
Please go. Please go.
It's very technical one, but basically, what compiler does, it usually converts your code from the high-level language to the low-level language. For example, like in C++ will be converted to assembler. But transpilation is much different. It actually converts maybe the code from one level and to the same level of abstractions. And you shouldn't be thinking that transpilation is much more easier. Usually, compiling to a low-level language is simpler.
Okay, there you go. That's the quick answer there. All right, I had a question actually. So I put it in the chat, but I'll just read it off here. So Haiqu's partnered with the Perimeter Institute, mostly like Roger Melko's Pickle branch of Perimeter. that was announced recently. I can't remember if it was last year or early this year. But anyway, Roger was here last week to talk about open quantum design. And I can't remember in his presentation if he mentioned Haiqu at all, but I'm wondering if Haiqu has a role in what open quantum design is up to, and can you comment on that partnership?
Yes, so we are joining the open quantum design, but I think this is a fairly fresh subject. So I'm not sure if we already officially announced this as the partner. So that's as much as I can tell you on this.
Oh, okay.
Unless Yura is able to share a little bit more details on this. Correct me if it...
We want to work on other open source initiative in part of this project.
Mm-hmm. I see.
Okay.
So the short answer is yes, we'll be actually joining, but this is in the working.
Cool, interesting. All right. Right. Okay. There was a question from Gloku42 again about the GitHub repository. It's on the screen right now. I'll just put that up there on the presentation.
Oh, sorry.
Yeah, just about like where the.
I missed the slide.
It was the one you had up.
It was here. It was this one.
Yeah, it was that one. Cool. Yeah, that's where to go. Scan those QR codes right now. I'm gonna take them off the screen in 3, 2, 1. Okay, cool. We have another question on Twitch from Raftersaurus. For the middleware stack you guys are developing, how close to the hardware will you eventually need to run? Can all this happen on the user side, or will you need to do some collocated execution with quantum hardware?
No, that's actually a great question. So that's one of sort of the fundamental things that we're thinking about, and the way the system is set up currently, and you have to understand that we're of course a very young startup, so we're moving very fast, but there's only so much we can do. Is we're working on the higher level. So we're currently thinking of hosting most of the compute intensive things in the cloud. But of course, for future efficiency, one will have to move closer to the devices and also think of co-located solutions. So that's something that we're thinking about, but that is not part of what I've been advertising to you right now. But it's, of course, it's an important consideration. That's actually a perfect question.
Cool. All right. We just had another question come in from Entiedo too. Can you elaborate more on the example of the Stack API? I think you had a slide with like 4 different, that one. Go ahead.
So as you may know, transpilation consists of different steps. Actually, there is a routing phase, layout phase, all different phases there. And with Stacks API, you could replace some of the phases there with the passes from different open source transpiler. And you may know that this transpiler works better on some of the features. And now you could build your own transpilation pipeline using these passes from different transpilers. And like just maybe you just simply, maybe in simple case, you may just want to transpile with different transpiler with one API. And you could want to test how it works. I think it's something that you could start with right now even.
Cool. I have one more question too. I asked this yesterday to Jinsung from NVIDIA. There's quite a bit of I think the theme this year of this QHack is like compilation. Like that's the next big thing in quantum programming, I think. So would you guys say that if people are looking to get into quantum programming, is it more worth your time? Obviously do whatever you enjoy, right? But is it worth your time is it more worth your time, to like learn LLVM or something, or MLIR or something like that, instead of becoming a Python ninja now? Like what's your guys' take on that?
Well, I mean, I can tell you that LLVM that's really getting to like level hard maybe, but of course if you do that, then possibly we'll be able we'll be very happy to talk to you.
Right.
So actually it's probably a great idea for your employability, because that's actually a really hard skill. Like there are no, in general in quantum computing we have a bit of a problem of shortage of people with specialized skills. Traditionally, the source of pretty much everyone in this industry are actually university departments of condensed matter, both experiment and theory, and people involved in numerical methods. Maybe more recently also people coming from AI. But if you want to acquire such specialized skills, I think they're probably they will be in short supply, and you'll be very successful. But on a kind of like less hard level, I think this is actually a super cool area to get into, because on one hand it involves some very nice algorithmic and software engineering challenges. So I think it should appeal to people coming from this background. But on the other hand, if you look at various solutions available, for example, in the context of error mitigation, I think they're also very interesting from the scientific point of view. So if you're coming from like a more academic, theoretical background of condensed matter physics, that's also very nice. And I would say it is probably more interesting thing and more practical thing to get into, the current industry and the current startups and so forth, than just learning to execute, let's say, Grover search in a kind of, idealized setting, and trying to say that you're going to solve like some, finance problem.
Cool. All right. That was a good answer. Thank you for that. One more question from Guillermo in the chat here. You've shown several times topologies of IBM quantum computers. So from your experience, does this structure make sense to facilitate transpilation?
So we are, we obviously, looked at IBM because, IBM is pretty much the gold standard there is. And the topology is dictated by physics, right? It's a superconducting device. There are of course other devices being developed that are based on entirely different physical platforms. And they all have their other advantages, and it's a little bit of a question that I'm not sure if one can seriously answer like in full generality, because it's not like IBM actually has the choice to to do an all-to-all connectivity with their their physical system, right? So I think it's a trade-off, and I will certainly not be as arrogant to claim that I would have chosen a better topology than the heavy hacks that they've done. But of course, topology influences everything, but it is dictated by other constraints of your physical platform.
Right. Okay. Well, hopefully that answers your question, Guillermo. I think we'll leave it there. If you guys do want to learn more about Haiqu, maybe you guys could show that slide again. Oh no, it's up already. Cool. With all the with your website, go check out our job, the QHack job board as well. There is a listing on there from Haiqu.
Yes, and of course, if you are interested, please contact us. There are various channels. You can go via LinkedIn or via the website. And if you do actually check out the Revit compiler, then they will be super happy if you provided some feedback. And if God forbid some bug appears, that's also super welcome. So enjoy.
Right. All right. Well, Maciej and Yuriy, thank you so much. Looking forward to see what Haiqu's up to in the next year. Maybe we'll be back next year at the next QHack to tell us about some more cool stuff.
We hope so too.
Yeah.
We hope so too.
All right.
Thank you.
Thank you so much. Have a great rest of your day and take care. Alrighty, so we got a lot of more talks coming up here. Next, we have John Malcolm from Multiverse Computing, excuse me. He's going to talk about singularity foundations for optimization and AI. So that should be fun. So that's at 11:30. We ended a little early with Haiqu's talk, but that's totally fine. Maybe a good chance to go grab some more coffee, another snack. I'll be doing that as well. So stick around, lots more coming. We'll be back in about 13 minutes. All right, welcome back, everybody. We have more talks coming up here. So we have John from Multiverse coming up next. And with that, let's just get right into it. So John is the Chief Technical Product Officer at Multiverse Computing, responsible for overseeing the technical aspects of product development. John holds a PhD in condensed matter physics. I have a master's in condensed matter physics, so hello, fellow condensed matter physics person. From the University of Guelph. Oh, from Waterloo, so very close. Tri-City area, although Guelph is never included in the Tri-City area. Shame. And John spent many years performing model validation at a large financial institution in Toronto before joining Multiverse. So, John, how's it going today?
Hey, pretty good, Isaac. Thanks for having me. And yeah, that's right. Over in Guelph, we would always refer to it as the Royal City, Tri-City over next door.
Nice. All right.
But yeah, thanks for having me. So as Isaac said, I'm the Chief of Product over here at Multiverse Computing. And so what I wanted to spend today is first just introducing the company Multiverse Computing to our audience, and focus on a couple of our products, our low-level products that might be of interest here. Yeah, let's dive right into it. So who are we at Multiverse? So we're a quantum software company. We're globally recognized. We're a global company itself. I'm here based in Toronto, but we have offices. Our biggest office in Spain, in San Sebastian. We have an office in Germany, in Paris, France, in the UK, and like I said, here in Toronto, our next biggest office. But not just being located globally, but being recognized globally. Last year, we got a nice accolade from CV Insights saying that we're one of the top 100 AI companies in the world to watch out for. So while we are, we present ourselves as a quantum software company, that's really just about how we achieve what we do using quantum technologies. But what we offer is really in optimization and in AI, which I'll dig into later into the talk. We're a growing company, so we have currently, I think, around 140 employees. From when I joined a couple years ago, I was employee 20 or something like that. So we're growing fast. We're very productive, having a lot of papers, a lot of patents, and a lot of partners in industry to develop our software and to create solutions that are relevant today to industry and to generate value today. So we hear a lot about quantum. It's still nascent. It's maybe 5 or 10 years when we have those fault-tolerant computers. That's when we'll be able to generate value with these things. But here at Multiverse, we found that actually with today's technologies, we can find those opportunities for generating value in industry. While some of them can be particularly niche, it's important for anticipating when that huge boom around quantum will happen when those fault-tolerant computers arrive. So where other quantum companies, you might hear them talking about quantum advantage a lot, we talk instead about business advantage, because that's what's really of interest to our clients, our customers, our partners, is what value can be generated for that business using today's technology. So here's just examples of some of the partners that worked with in many different areas. So we can see we have applications at all sorts of different industry verticals, from starting out in finance, but we've branched out into manufacturing, into energy, healthcare, cybersecurity, all sorts of things. And you can see probably some recognizable companies in here. Bank of Canada is a big one if you're here in Canada. A lot of European companies as well, coming out of our office in Spain, and in all of these different areas. So how are we able to offer so many different applications across so many different verticals? So this is how we're set up. So up in the top corner, Singularity. This is what we refer to as our entire software suite. So it's the Singularity software suite, not just one individual product, but a collection of many products. And then Singularity can be bundled into to different vertical focused packages, like Singularity for Finance, where we have all sorts of financial applications, portfolio optimization, index tracking, FX trading, derivative pricing, but then we also have singularity for manufacturing, singularity for energy, for cybersecurity. And what allows us to have all of these many different use case applications is that they're all based, leveraging the power of our core foundational engines, our foundations products, in optimization and in AI. So, so two of those core pieces that we show on the slide here, and which I'll dig into one of these in more detail in a second. But I show we've got singularity optimization. So this is a low-level generic optimization package. It's available in Python, but other interfaces as well. And with this package, developers are then able to submit kind of a standardized, generalized optimization problem for solution by quantum approaches. So taking a specific use case problem like portfolio optimization, and then our developers then style that in a particular mathematical form that can be submitted into this generic solver, singularity optimization. We get the raw result out of that, and then again we reformat it back into the context of portfolio optimization. So it's really these core engines that are doing the big heavy lifting, and then that allows us to have all sorts of many different use case applications using today's quantum technology that are based on this optimization and machine learning routines. So it's another one we have listed here, singularity of machine learning. So so using quantum machine learning techniques, quantum deep learning techniques for all sorts of different applications within these different areas. These core engines themselves, they're also available as standalone products. So for other low-level developers that resemble the internal developers that we have at Multiverse. So those people at Multiverse that are using these core engines to develop these use case applications. And then, of course, we have a lot of developers here that are building these core applications, and that's where comes in all of the quantum engineering and a lot of tensor network engineering, which I'll elaborate on a little bit. So so we do try to, for our end user applications, so including our core packages, and then especially, of course, our use case applications, we try to avoid anything that requires any sort of quantum expertise. So we don't include much quantum jargon at all, other than to say, like, yeah, it's powered by quantum techniques, quantum computing. But we try to make a package like SOP or singularity optimization familiar to people who are used to optimization software, but maybe really unfamiliar with the world of quantum. Similarly with machine learning, and of course with something like portfolio optimization, we don't require asset managers to have a degree in quantum physics to be able to use our tools. So who we do require to have quantum degrees are developers in-house at Multiverse, and they're the ones that are connecting our software to various quantum hardware that's available from our partners, including Xanadu, but also D-Wave, IBM, IonQ. And then we have a lot of in-house specialists on tensor networks. So this is referred to as a quantum-inspired computation approach. So if you're unfamiliar with tensor networks, this is a method of computation that was developed in recent years out of physics departments as a way to efficiently simulate quantum systems within conventional hardware setup. So what it does is, with using tensor networks, what you can do is sort of reduce that full Hilbert space, your 2 to the n giant space, down into a little corner by making certain approximations representing your quantum objects, your quantum states, using these tensor network objects. And then those approximations allow it to represent just that one corner of the Hilbert space where things are actually kind of useful and interesting, you know, like near the ground state, or showing certain symmetries that are relevant to the problem. And then that way we don't have to consider that whole Hilbert space, which is the massive bottleneck when trying to do quantum simulations on a conventional hardware. And then the idea is that, well, if I can use quantum systems to do novel computations, then why can't I use an efficient simulation of a quantum system to do computations? And so so that's what we apply here at Multiverse. We have some of the world experts on tensor networks here at Multiverse, and we've been able to come up with some really novel and powerful routines in this these two domains of optimization and an AI that not only act as a stepping stone for when real pure quantum hardware can kind of catch up with the capabilities in terms of number of qubits that it can handle and all of that. But then tensor networks is itself really driving forward a lot of what can be done in computation, powerful computation. So just like where tensor networks are quantum inspired, and we can then develop algorithms out of that, at a certain point when quantum starts to catch up, I imagine that a lot of those developments are going to be inspired by developments that happen in tensor networks in this near term right now. So we're very comfortable with leaning on tensor networks and considering this as part of that quantum atmosphere. Now, knowing the audience that we have here at QHack, I would imagine that this is kind of the level that definitely the QHack participants would be interested in developing at this level, connecting directly into quantum hardware. Whereas, like I said, our packages that we develop are intended more for users who don't necessarily have that quantum expertise, but do can benefit from the power of it. So we have maybe about 5 minutes left. So I wanted to just quickly zip out of these slides that I prepared and instead switch over to some actual code that I can show you. And so here I'm going to demonstrate an application of singularity optimization on an example of an optimization problem. So here you can see the package that I'm using. So I'm in a Python framework for this presentation right now. So we import singularity optimization module. So you'll see it throughout the code represented as SOP. And then the problem that we're going to be tackling is an analog to the traveling salesman problem. So if you can see this computer chip circuit, so imagine that you're working at a computer chip production company, and you need to drill holes in this computer chip, and then the next one comes in, you need to drill holes in that, and so on and so on. So you want it to be done as efficiently and quickly as possible. So I need to drill all of these holes that are marked on the board, and then I can automate, okay, what order should I drill these holes in? And so then it becomes, like I said, it's pretty much that traveling salesman problem. So I need to have my drill visit each of these locations once and exactly once. So I can't go back to the same place and drill a hole again, because that would just be inefficient. I don't need to drill it twice. But all of these holes do need to be drilled. And this is actually a computationally challenging problem. It's well known that traveling salesman is difficult. And so what we do in this example is we style the problem as a QBO. So many of you might be familiar with that. So that's quadratic, unconstrained binary optimization problem. So that's one type of standard format that optimization problems can be represented as, one that's most directly applicable to many quantum routines, like the Ising models underlying quantum annealers like D-Wave, but then also variational approaches using gate-based computers, QAOA, will work on solving QBO type problems. So if I quickly speed through here, so you can see some of the code is first just representing the problem. Okay, what are the different drill speeds in the different directions? Let me give it a function to determine the distance between each of the points. Next here comes in SOP, so I'm just going to declare, instantiate the variables, my binary variables, since we're creating a QBO problem, although I can do integer variables with SOP as well. So here the way that we're doing binary variables is that, all right, so for every position, I'll have a variable based on its location, and then also what position is it in. So if I have that spot that I need to drill and I label it number 15, which would be the job, is that the first drill hole that's drilled? Is it the second? Is it the third? Is it the fourth? And so on. So then I would have a binary variable for each of those. And then only for spot number 15, only one of those should be 1, the rest 0, which would indicate, okay, for that one variable that's a 1 and not a 0, then that would indicate that job 15 happens at that stage in the sequence. Now, using that, then I'll zoom down here, and I use these variables to construct a cost function. So the function that I'm trying to minimize, which is the total time spent for my drill moving around. So that includes the distances between each of the drill spots, and then these different variables, whether or not that drill spot happens at that time, yes or no. So that's 0 or 1. So this is what we refer to our objective, or our cost function, which we're looking to minimize. But a really important part then is putting those constraints. So if I just minimize this cost function, well, very easily I can just set all variables to 0, and then that would definitely minimize it, but this would not be a viable solution. That would be telling me, hey, don't drill any holes in this hole. So we have a lot of constraints that also get submitted along with it. So each job needs to be done exactly once, and at each point in time, I can only drill one hole. So those constraints then get combined with the objective into an optimization model. So this is like a pretty familiar approach to coding for optimization type problems. You'll notice that there isn't mention at all of anything quantum in here. It's just, hey, what's your objective? What are your constraints? All right, let's use our quantum solver to do it. So we've prepared this model. Now we're going to optimize it using our quantum inspired method, and then just sort of print the results. We have another method in here using a greedy solver technique just for comparison. But well, I'm running out of time in this presentation, so I won't actually, run this code right now. I can jump to some results that presented earlier, or prepared earlier, sorry, before this call. So you can see here, okay, running the circuit will start, or the drilling. This is the optimal path that comes out of it from our SOP tool. So hit all of these locations in this order. So we've got it plotted out here, but of course it comes out as a convenient dictionary or list, or however the user might want to style it and integrate it into their own workflow. Okay, so I know it's a short time to try to present Multiverse and all that we do, but I hope that this was a good representation of those things, and it captured your interest. But with that, maybe I'll wrap up and pass back to Isaac for the Q&A portion.
Cool. Thanks a lot, John. That was really interesting. Thanks so much for that. We had some questions, so let's try and get to them here. We had a question from Entayido. John, what is the sample or data size of the file for the optimization of the SML approach?
Right. So we can handle very large problems. The size of the problem with our particular SML routine, or at least one of the classification routines that we have in mind, that I have in mind, that we use greatly. It's not the data set that is represented with quantum bits. So our machine learning techniques, I'll step back a little bit. We use a hybrid approach, and we use hybrid approaches in a lot of what we do because of the limitations that exist in current technology, quantum technology. So like with our machine learning, our quantum enhanced boosting technique, there's one intermediate step that's carried out using quantum techniques, but then the rest are still using classical conventional approaches. So with that classification thing, it's not limited then by, or like the quantum step is not limited by the number of the data set. It's more about the accuracy of the model that you want to come in. So it's an ensemble learner approach, and so it's like the number of weak learners that are represented by qubits in there. So that's kind of the limitation. So, but going up to excuse me, losing my voice, up to 100 or more qubits, we can definitely handle that.
Cool. Okay. There's a couple questions that are coming in right now. Like, how do I begin with the qubit model in finance, or like, what are the resources? Where can people go to learn more about Multiverse?
First off, go to our website, multiversecomputing.com.
Okay.
We have a lot of literature that's available on the archive. So you could go straight to the archive. You can go to our website, and all our papers are listed. And while some of our things we keep close to the chest, so we don't share all of our proprietary techniques, but many things are shared in that literature, including how we, for example, take that portfolio optimization problem and represent it as a qubit. Honestly, that was the thing that got me so excited about Multiverse when I read that paper. So my background, I come from condensed matter physics, so I'm familiar with the Ising model. And then I worked for a number of years in finance, so I'm familiar with portfolio optimization. And then to see, oh wow, portfolio optimization represented in the icing model, and then I could just do this by finding the ground state of that. And I got super excited, and just rushed over to the multiverse.
Yeah, definitely. The Ising model can be applied to like 7 million things. Like,
Right.
This was like right at the start of the pandemic, but I even thought I saw like a paper about like something about COVID-19 and like the transverse field Ising model. Somebody wrote a paper about that, and I had a good chuckle over that. The transverse field Ising model has been beaten to death. Okay, question from Kentucky Kirby. How does Multiverse interface with, or does it interface with other packages like Qiskit or Penny Lane or anything like that?
Yeah, so that's the part where I was talking about like behind the scenes within our core engine. So that's the work that our internal developers take care of. So having this generic interface, and then we like to say that we're hardware agnostic. So in the back end of our tools, then we prepare all sorts of different routines so that we can very easily swap out the different solvers for our end user, who can just select from a drop down menu or keyword argument. So then in that back end, if we're using Xanadu or whatever, or IBM's computer, then we can have things based interact with Penny Lane or via Qiskit. We do have on our roadmap too, and whether how interesting this is to potential users can sort of accelerate that on the roadmap, but having allowing those deeper low-level quantum engineers to interact with our products so that they could themselves be working in a Qiskit environment and make use of our tools and sort of integrate things at that end user level as well.
Cool. All right. Well, that's all we have time for. But John will be on the Discord after this as well. So if you do want to have a chat with John over the course of the duration of QHack, please do so. John, it was great to have you on here. Have a great rest of your day and enjoy this. Looks like the sun has disappeared for us here in Toronto, but enjoy the rest of your day.
All right. Back at you. Thanks very much.
Cheers. All right, everybody. Next up, we have Jarrett Smalley from Rolls-Royce joining us. So that'll be in about 10 minutes. So don't go anywhere. After Jarrett's talk, we will have a break and a giveaway. So stay active in the chat, and you could win some swag. And then after that, break, go get some lunch, have a snack. But yeah, we'll be back in about 10 minutes with Jarrett Smalley. Cheers. All right, everybody, welcome back. We have Jarrett joining us from Rolls-Royce. So Jarrett is a quantum computational science specialist at Rolls-Royce. Jarrett's worked with quantum computers for 7 years in industry and academia, and now focuses on the future applications of quantum information in designing power systems and optimizing networked interactions. Jarrett, it's lovely to have you with us today. How's it going?
Yeah, thanks, Isaac. Yeah, it's going well. So
I don't know what happened, but so you're appearing twice for me in this little. It's not your problem. Something's happening with the stream, but double the Jarrett right now. But the floor is yours for your presentation for quantum computing with power systems. So go right ahead.
Okay, cool. Yeah, no, thanks again for having me. This is a pretty cool situation. So yeah, today I was just going to go over a little bit of what we're doing at Rolls-Royce with quantum computing. Yeah, just kind of, and a few of the algorithms that we're kind of focusing on. So here I just have a picture of the Ultra fans. This is a demonstrator of, I think, what's going to be our largest like turbofan engine that we've ever made. So we have one of these, and I think we're hoping to get some airlines interested in these in the future. So so yeah, I'm just gonna run through a little bit of Rolls-Royce, this company that I'm doing quantum computing for, a little bit of some of the applications that we are interested in, and then a few different quantum algorithms that are specifically targeted at a few of our applications. So so at Rolls, we have 4 main business units. So civil is where we do a lot of the stuff that we're known for, which is where we do actually we make the jet engines that are on commercial aircraft, and so that's a big place. We also have power systems, which is doing everything from, like, I think, trains to kind of like local power. We also have a defense unit, and then this latter one is where it's a newer thing. We're doing small modular reactors. These are smaller nuclear fission reactors that are targeted at, I think, like smaller towns and eventually powering like warehouses and factories. And so yeah, between these all, we have a lot of different engineering going on. So we have like within this, we have a lot of quite a few numerous like challenges. And so here we have just like a cutaway of one of our engines. And so where the air is of course starting, I guess, on this left area, or maybe it's over here, is left for y'all. And the air it goes through the intake, and then we get it compressed down. Then we have a state of combustion that then is shot out the back. And this is what kind of powers, not just kind of, it powers a lot of our flight all throughout. So on a lot of our engines, we have between, I think, it's like 25 to 30,000 individual components. And so each of these have to kind of be machined, like precision machined to very specific tolerances. And they also have to, they undergo like crazy forces. And so one of these that I think is always a really cool thing is our the turbine blades that actually sit in the combustor. So like in this, not in the combustor, in the compressor. So like right in here, they have fluids flowing around them. So we make them so that they have fluids flowing around them that where the fluid is hotter than their melting point, but then we cool them from the inside. So you can see these little holes in here. So these are some pretty intense devices, and not just devices, but yeah, just engines that we have going on. So to design these engines today, we use a lot of supercomputers to do our modeling, but we see that these eventually in the future are going to start like kind of trailing off, and so we are interested in quantum computing, and so that is both what I do and also I guess why I'm here to talk today. A lot of times, at least in the past, we within quantum computing, right, we had this idea of these noisy intermediate scale quantum devices, and so these are devices that we have today that are awfully noisy and maybe not the most useful for things that like we care about, because we just can't really deal with the noise, and also a lot of the algorithms that we care about need tens of thousands of qubits running many millions of operations even. So we're kind of targeting more of the fault tolerant era, where we have way better quantum computers, and so that could be. I think a few companies have put this within this decade, though others are pushing this off for a couple of decades. So we'll see how that that goes. But while we're getting to fault tolerant, we are still involved in developing towards that era. So we're involved in a few different programs. So Rolls-Royce, as Rolls-Royce, we're involved in a few different quantum programs. Most of them are through the UK's Research and Innovation hub, specifically through the National Quantum Computing Center. And so, like one of these projects is we're kind of just trying to get the full scale, like what the entire throughput will look like in the future of going from the problem that we're dealing with to kind of the compiled circuit that we're going to be looking at to even running it on the quantum devices. And so that's with that's this QEC project, this quantum error correction project, and so that's with Universal Quantum and Riverlane. And then we also have another project with Xanadu. It's between Canada and the UK governments, and so that is kind of targeting a little bit of the compilation steps with one of our algorithms. And we also have other project where we're targeting material discovery. And so that specifically, I think today we're looking at, not just I think, we're looking at like hydrogen embrittlement. So when we're trying to develop hydrogen engines for the future to have cleaner engines and just more sustainable fuels, and just like what that is really going to do to the engine itself. We also are involved in a number of just like smaller scale projects. And so these are hackathons, kind of similar to this kind of thing, but I think a bit smaller scale. We've been involved in both of the NQCC's hackathons. We do small projects with various startups like Classic and Xanadu, and we also fund PhD work. So yeah, we've got kind of stuff all over the board. Yeah, so I'm going to be talking about a couple of our applications that kind of are united within themselves. And so one of these is computational fluid dynamics. And so I think I've got like a video that we can probably post in the chat because this one is not going to be able to run. But we model the fluids that are going on inside, like the fluids, the movements of the fluids inside the engine up to a scale of 4.6 billion elements. And so that's just like dividing these down into a really small scale so we can kind of understand all of the different little like flows and like turbulences that are going on with the fluids to then understand kind of the stresses that will then be applied to the engine itself, and then eventually see just what an engine might be able to do. With this, then we also have hand in hand with this our finite element method modeling techniques, and so this is where we're actually looking at the materials themselves and observing how the materials will react to certain stresses depending on their formation, and then also just like the material itself. Here I just have like a cutaway of one of our FEM models of the full engine, and then also just kind of the 1D stiffness matrix for the stiffness matrix equation for like a single element that's like in a 1D situation. So these we piece these together. So if we have like 4 billion elements, we're going to need 4 billion of these that are then all coupled together, but then also in like a 3D situation. So we have some cool, we have a pretty intense computational stack that we're caring about. So both of these, CFD and FEM, they kind of go through a similar loop where we start with some kind of model, so like some new design that we have. And we're going to mesh that, so we're going to discretize it into a bunch of little pieces. So that's where this like 4.5 billion comes from. These like we're dividing it up into a bunch of little pieces. We then can translate those pieces into a series of equations. So it's like a linear system of equations, and then we end up solving that. And so that takes the form of we're like inverting a matrix, and so these matrices can be quite big. Anywhere from like millions by millions to even billions by billions, and so that's a really intense process. As I mean, just inverting a matrix is yes, it's computationally difficult, especially at that scale. And so this is solving this linear system is the bottleneck that we're really looking at, and we're hoping that in the future we might be able to use quantum computers for. So for this, there are a few different quantum linear systems algorithms, so like quantum algorithms that will solve these linear systems. And I'll talk about a few of those. And so one is the it's like more for the NISC era, and probably nothing that we'll be seriously looking at outside of hackathons, is the variational quantum linear solver. And so this is a sketch of a variation on that with the coherent variational quantum linear solver, which I believe there's a Penny Lane demo on the web of, put together by, I think, Andre Amari. And so this is, it's a kind of a standard variational algorithm. We have some parameters that we can optimize on in a classical like outer loop. But if we're actually running this on a quantum computer today, we have like loads of noise and like barren plateau phenomena that we would have to deal with if we wanted a good solution. And so we're probably not going to get to the 4.5 billion by 4.5 billion matrices that we're looking at today. So this, I think, is for like a 2x2. So one of the algorithms that we see as having the future potential is this HHL algorithm written, I don't know, I think it was like 2010, maybe 2008. Yeah, I think it was 2008. And so this is a fault tolerant algorithm that really takes advantage of a few different subroutines that have been fundamental in quantum computing. And so for this, it's kind of a simple circuit that I've drawn out here. So we're loading in, we're doing some we're loading in the B vector in our linear system of equations. And so this is where we have like state loading. And so that's kind of a thing that we do. We then use a quantum phase estimation to express that B vector in terms of the eigenvalues of the matrix that we care about. We then want to, we're going to invert them, these eigenvalues, because that is somewhat equivalent to inverting the matrix. And then we will go back, use an inverse of the quantum phase estimation to go back into the basis that we care about. So it's a pretty simple algorithm. I just have a tricky little thing where based on this, we need to, at the end, be measuring in the one state. And if we don't, we can just like keep rerunning this main circuit until we eventually measure a 1. So we don't actually have to measure all of these guys. We just measure this one and then maybe rerun the circuit. Yeah, this has a not horrible complexity. I mean, it also was the first quantum algorithm for linear systems, and so it scales yes, quadratically with the with kappa, which is it depends on the eigen spectrum of the matrix that we're inverting. Yeah. So we also have this newer algorithm, and so this is where we've put in a bit of time, and that a few of our programs are really working on today. And so this is the quantum singular value transformation. And so with this, it takes like kind of quite a bit of a different form. So we just take the matrix, we're inputting it into this algorithm along with some polynomial, and then these will give us a transformation of the matrix, or the matrices singular values. And so for this, there's a couple of subroutines. So in quantum, as we probably all know, we need to have unitary operations. We need operations that we can reverse, essentially. And so for this, we can't just have like we can't just put any matrix onto the quantum computer itself. We have to take the matrix and put it into kind of what we do in the quantum singular value transformation is we put the matrix itself into like a block of a unitary. And so that's what I'm kind of representing right here. And then we can not care about the stuff that's going on in the rest of the unitary, but we're really caring about this little bit right here, because then we can operate on it in a very specific way. So in the circuit itself, there's a few different ways to do this, and one of these is having like a linear combination of unitaries, and so that's kind of what I'm representing right here, which can scale kind of in a crazy way, and the compiling to do that is an entire other situation. But yeah, Penny Lane has a couple of cool demos on this as well. So we couple this then with a technique extended from quantum signal processing, which is where we have we have like a polynomial, some polynomial that's estimating the transformation function that we want to apply to the matrix itself, and we decompose this into a set of phase rotations on an ancilla qubit in our circuit. And so actually I have the circuit in the next page after this. And so what we're trying to do is we're trying to estimate the function on some like area. And so this is the inverse, right? And so when we have one of these polynomials, we're getting close to that, at least in the regime that we care about, because we're saying we don't really care about this. So to find these phase angles, there's a few different ways to do this. Luckily, there's just some good GitHub repos that allow us to do this. Also, there's a great PennyLane demo on quantum signal processing. So we can put this all together into a circuit that looks something like this. And this is not just for matrix inversion. We can do all kinds of other things like amplitude amplification and Hamiltonian simulation, depending just on the phase angles, essentially, that we have up here. And so we can apply many different functions to our matrices based on like one kind of circuit, essentially, just changing the rotations that we have. So this is a really neat algorithm. It has a better query complexity than the HHL, and so the query complexity is like how many times we need to implement the matrix itself. And then if we're not just estimating the inversion function, if we estimate a kind of similar function, we can actually get that down to an even better complexity with a few neat tricks. So the steps to actually getting this onto a fault-tolerant quantum computer, like even if we had one today, we wouldn't probably be able to do much with it. So because of the fact that we still have to tackle a few of these subroutines, especially in the large scales that we're caring about. And so some of the things that we're focusing on in those projects that I was talking about earlier are specifically the state loading, and then the developing. So this is like, loading in the actual state that we're caring about. So usually that B vector, or maybe if it's in one of these other, if it's for like another application, then yes, just loading in our starting state, because that's not always trivial. And then we have a few different other subroutines that we need to care about. So that block encoding bit, because that's not always straightforward, and having an optimized throughput for that is important, because even if we had like the fastest quantum, even if our quantum computer was almost instantaneous, I mean, it's not going to, right? But even if it was like really fast, the pre-compilation step might also be a bottleneck that we want to kind of be planning for, and finding different patterns in the data itself that we can take advantage of, so that our compiling isn't too intense. And then so we also want to find one of the other things that we're looking at is the class, some of the classical. So besides just like classically compiling, we want to find analogs to classical preconditioning, and maybe some other steps that we find in computational linear algebra that just like allow our algorithms to perform even better. So these are some of the things that we are focusing on today in our programs. Today we definitely are not looking at these very huge matrices, these like many billions of elements. Today we have a set of rather simple test cases. So whether like on the left, that's a 2D lid-driven cavity, and so like we have this lid that can lift up, and we have like the fluids moving inside of there. Or we have from the FEM point of view, we have on the right just a 1D like beam that has a force on the end. So we want to see how things move in there. And so these generate rather simple matrices, but matrices that might have like sparsities and a few other things that kind of translate to the kind of problems that we care about in the future. And so these are where we are kind of today, and these are the problem instances that we care about today. I don't have too much else to talk about. So this is I don't have too much else. This is I think an artist rendering of one of our hydrogen engines. So I think we, like mid last year, I think in the autumn of last year, we actually had one of our demonstrator hydrogen engines run for the first time, at least in public. And so we're really pushing towards this like idea of net zero and having cleaner engines in the future, because that would be just really important. It's really good for the environment, so, and the globe. So I don't have too much else. That's all I have really to talk about. But otherwise, Isaac, I don't have too much else.
Cool. All right. Thanks so much, Jarrett. We had a couple of questions. I think we just have time for one here, but let's get to one. It is from Davidren_Twitch on Twitch. Is Rolls-Royce pursuing a hybrid quantum classical approach for solving the linear problem in CFD, or is Rolls-Royce pursuing a pure quantum approach? I think I know the answer, but you can take that. Cool. All right. Well, Jarrett, it was lovely to have you. For those wondering, the Open Hackathon is open, and Rolls-Royce is offering to meet virtually with a winning team. So definitely participate in that. And maybe, I don't know if it's you, Jarrett, or somebody else, but that'll be interesting. Jarrett, thanks so much for joining us at QHack. It's lovely to have you with us today. Enjoy the rest of your day. And yeah, take care. Cheers. Okay, everybody, we're going to go on a short break. We'll be back at about 1 p.m., but we do have one important business matter to take care of, which is the aforementioned giveaway. So in the chat, if you are active, you will be entered automatically to win some swag. So let me see here. Let's wait a few more seconds. Wait for some more people to come in. I'm going to roll this. 5, 4, 3, 2, 1. Roll it. David Duran _Twitch. You have won the giveaway. Congratulations. You are going to be the proud owner of some swag. Congratulations. One of our moderators will get in touch with you about getting your information so that we can send you this awesome swag. So be on the lookout for that. Up next, we have some nice stuff. We have Efrat from NVIDIA coming to give a nice long talk about getting started with CUDA Quantum. So that'll be really fun. Then we have some jam-packed action in the afternoon that you don't want to miss. So grab some lunch, get another coffee, a snack, whatever you need to do. Don't go anywhere. We'll be back in about half an hour. We'll be hanging around in the chat, too, to answer any questions should you have them. Again, the Open Hackathon is open, so go to QHack.ai and check that out. I think there might be some issues with accessing like the actual tab on the website. I think our developers are working very tirelessly to make sure that there's no issues there. If there are any issues, though, feel free to open a support ticket on QHack.ai, message us here. Yeah, whatever you need to do. I think that should be fixed relatively soon. So we'll see you back here at 1 p.m. Eastern Time. Enjoy your lunch, your breakfast, your dinner, wherever you're joining us from. See you at 1 p.m. Eastern. All right, welcome back, everybody. Appreciate you coming back. I wolfed down some lunch, and I'm ready to go for another afternoon of QHack talks. So up next, we have Efrat from NVIDIA. Efrat is a senior product manager for CUDA Quantum at NVIDIA. Prior to NVIDIA, Efrat worked as a principal engineer manager at Microsoft, building innovative products in Azure Quantum, Microsoft Research, and Azure Machine Learning. Efrat holds a Bachelor's of Computer Science from the Technion Israel Institute of Technology. Efrat, it's lovely to have you with us today. How are you doing?
I'm great. Thanks for having me.
All right, so you're here to talk to us about getting started with CUDA Quantum. I'm really looking forward to this. So the floor is yours.
Thank you. So welcome, everyone. Thanks for joining me today. Today, we're going to talk about, first of all, what is CUDA Quantum, and then get into some code examples of how you can scale your code and get speed up. We'll talk about some simulators and backends that CUDA Quantum supports. We'll touch on VQE and noise modeling. At the end, I'll share some resources that will be helpful for you during the hackathon and some specific hackathon instructions on our environment. So let's get started. So really, quantum computers will accelerate some of today's most important problems, but CPUs and GPUs will still be needed, and workflows will be hybrid. GPUs can also enhance the performance and development of QPUs and can run quantum simulations at scale. And that's exactly why we built CUDA Quantum, for developers to seamlessly be able to integrate these heterogeneous computes and accelerating supercomputing. So CUDA Quantum is really a single source Python and C++ programming models. It has high performance compiler for this kind of hybrid systems that I was talking about. It is QPU agnostic. It works with any types of QPU, whether it's emulated or physical QPU. And it's interoperable with all the leading scientific computing and AI tools and libraries that you already know. And it's really built for performance. So it will perform significantly better than alternative Python frameworks. This is one example of VQE of hydrogen chain, but you can expect some significant improvements in terms of performance. Okay, so let's dive into some code examples. Let's start with a simple example, a GHZ state, where 3 or more qubits are being entangled. So here you can see the Python code within CUDA Quantum that describes that. So really, the first thing that you will see is something called a kernel. A kernel is a piece of code, a unit of code of program that can be compiled and run on various devices. The kernel here gets a number of qubits as parameter, as you can see, and entangles them using a control XGET, and then performs a measurement using MZ. And then we call sample over the kernel, and it's been sampled multiple times. 1000 is the default. And then for n equals 3, you can see that's kind of a typical output that you might get. Either all of the qubits will be 0, or all of the qubits will be 1, and there'll be some distribution between the different samples. So that's great. That's, the previous examples ran on my CPU within a few seconds, and I was able to get the results. But what if I want to run more qubits? So the only thing I need to do when I'm writing CUDA Quantum is really change just the number of n to be 29, and then set a specific target. As you can see here, target equals NVIDIA means I'm going to use my local GPU. I have a GPU on my laptop, and I'm able to run this code with just adding this line. And I'm able to actually simulate 29 qubits on my laptop, on my GPU that I have on my laptop. So that's great. I didn't need to make a lot of effort, and I'm able to immediately scale this example. But what if I want to scale to more than one GPU? You probably know that there is an exponential scaling of state vector that requires GPU memory pooling to simulate systems of about 32 qubits or more, depending on the GPU. And in order to do that, we have a target called NVIDIA-M GPU. And here you can see a table of an estimation of how many GPUs or how many nodes of GPUs you will need in order to run different types, different number of qubits. So we talked about scale until now, scaling the memory of a vector size to a GPU or more than one GPU. Now let's talk about parallelization. Parallelization is really a way to emulate multiple QPUs and running workloads in parallel in order to achieve speedup. So in this example, we're talking about a Hamiltonian. Maybe some of you are familiar with that, but Hamiltonian is a function that describes the total energy of a dynamic system as a sum of terms. It's used in many fields around chemistry and some other fields in order to calculate the Hamiltonian terms. But the advantage here is that they can really be calculated in parallel. So let's look at this code. Here is a code. In this code, we're creating again a kernel, and then we create some random Hamiltonian with random terms, 10,000 terms in this case. And we're using a target called NVIDIA-MQPU. And that allows us to simulate that on multiple QPUs, emulated QPUs in parallel. You see also the observe function here, and observe calculates the expectation values of the Hamiltonian batch, the terms, and distribute them over the multiple QPUs that we have. So if we run that on, in that case, a single node, single GPU, we're getting some output of the expectation value. And then we can also call that in asynchronous fashion. So if the queue is long, if the computation takes longer time, there's a way to call that in async form. And there's a way also to specify specific execution parameter, whether you're running on a single node with multi-GPUs or a multi-node with multi-GPUs. So you can really speed up, basically calculate all of these terms in parallel and achieve speed up. And there's also a way to combine both approaches, scale and parallelization. That's a new target that we recently released. It's called remote MQPU target. And for example, in this illustration, you can see how each pair of GPUs is an emulated QPU. So in this case, each GPU has 80 GB of memory. So together, each node, each QPU has 160 GB of memory. So we can simulate that size of state vector, but we can also run it in parallel. So if sequentially this type of computation would take 1 hour, in this type of diagram, it will take only 30 minutes for each emulated QPU to run the workflow. So until now, we talked about just state vector, how to scale that, how to speed it up. So that's one type of simulator that we have in Q-Quantum, a state vector. It is in Q-Quantum, Q-StateVec. And you saw that it's limited by memory, right, exponentially to the number of qubits. So these are the targets that we already seen, NVIDIA MGPU, NVIDIA MQPU, and remote MQPU that combines the both. We also have tensor network, so it uses Q-Quantum, Q-TensorNet. It can simulate thousands of qubits in cases where we see kind of a sparse or low entanglement problems. So for some problems, this can be a really great way to simulate them. And it can also run on multiple GPUs. And we have matrix product state, so MPS, which is an approximate tensor network method with the target of TensorNet-MPS. In addition to all of the simulator, we also have integration with QPU providers, so Quantinuum, IonQ, IQM, and OQC, and there'll be more coming. Another thing that is very useful is the VQE algorithm. Again, it's used for quantum chemistry, quantum simulations, optimization problems. In this example, you can see the VQE here is in order to determine the ground state energy of a physical system. Here it's an H2 molecule. But what I want you to notice here is that you don't need to write everything from scratch. In Q-Quantum, you have some elements that you can use, like the VQE primitive. You can use different types of optimizations. Here you see the Kobilac optimizer. We have some other optimizers, and you can also have some function of creating the Hamiltonian and so on. So writing something like this becomes easier with Q-Quantum. There's also a way to do noise modeling. So until now, all of the examples that we saw, we're assuming perfect qubits, but we know that real qubits are noisy, and we sometimes want to simulate them, simulate the noise. So in this example, this is just one example of a bit flip error that we can do with CUDA quantum. So here you can see we are defining a bit flip channel with one probability of flipping, meaning it will flip every time. And then we define a kernel that performs an X gate on the qubits and then measures it and sample it again, like we saw before. But we add the noise model in this time. So the qubit here was initialized to 0 state, but then after the bit flip, it would be in 1 state. So when we perform the X operation again, it will be measured at zeros, and you can see here the outputs. And then also I ran the same thing without the noise, and you can see that we got 100% of the time. So without the noise model, bit flip wouldn't happen, and we'll get 1 all the time. So this is just one example. We have different types of noise models in CUDA quantum. Basically, all of the cross channels operations, we support them. Okay, so that was kind of a quick run of some code examples in CUDA quantum that will help you to get started. I have a list of links here. I'll also paste them in the Discord channel. I think that would be useful, where you can get the CUDA quantum Python wheels. Like I mentioned, we're an open source project, so I have the link to the repo. You can take a look at the code. You can report issues and kind of see open issues there. We have documentation. I have the link here, API reference and language specification. There's some technical blogs that I shared there as well in our marketing page. And then on the right side, you'll see like the specific references to everything we talked about today, the installation, the multi-GPU workflows that include also the multi-QPUs, simulators and how to backend, the noise modeling, and some code examples and tutorials that will help you to get started. Yeah. So about the hackathon, we are giving the top 39 teams access to a Haiqu 100 with 80 GB GPUs from today afternoon to the 19th afternoon. And then the top 10 teams will get access to 4 GPUs. So these teams can really try all of these different multiple GPUs scenarios, and then you can get like real performance improvements. We have prizes too. So the first prize, you get up to 4 GeForce RTX 4090 GPUs, 1 for each team member, plus 2 weeks of support with Denver, our partner. And second place and third place, you can also get up to 1 GPU per team member. And the only thing you need to qualify is use CUDA quantum in your project, and just format the project with some abstract at the top. What the project does, why it is important, where you're using CUDA quantum, any performance kind of numbers or results that you think are interesting in the project, and we'll consider them for the prizes. And it's very easy to get started. So if you're one of the 39 top teams, you already got an email, you've got the password there, you just go to the link on the left, you just put your password, and then you have an environment that already has everything that you need. CUDA quantum is installed there. We have a couple of notebooks that with some examples that you can get started. And yeah, let's start hacking.
Awesome. Thanks, Efrat. That was really nice. Okay, we have some questions that I want to get to, so let's go right ahead here. We have a question from Dentucky Kirby. The relationship between CPUs and QPUs seems to be symbiotic at this point, I guess. Interesting choice of words. But what are the challenges, if any, with getting the GPU to QPU relationship up to par, or is there any compilation steps under the hood that are non-trivial?
So first of all, the getting into par, maybe specimen in terms of performance, but really GPUs are going to excel in some of the things, and QPUs are going to excel in others, and it's really about working together in order to achieve hybrid application. That's what I think. In terms of compiling, so we do have a compiler tool chain where we can actually emulate a QPU on a GPU. In that case, we're taking the CUDA quantum code and optimizing it in a way that would run on a QPU, whether it's emulated or a real QPU. I'm not sure if that really answers the question, but I hope that helps.
Yeah. If that doesn't answer your question, Kentucky Kirby, please respond back. Okay, we have another question from Panos Const. This is interesting. I was a Julia user in grad school, so this person might be a Julia user as well. Is CUDA Quantum supported with the Julia language?
Not at this moment. We're thinking about that or kind of extending it, but right now we support C++ and Python.
Cool. Interesting. Nice. I have a couple questions from my end too. So this is an open source project, which is great. One of the things, and I think this is something you hear a lot, and it's getting a lot better for sure. Dealing with GPUs can sometimes get like really, really hairy. So contributing, at least I found in my experience in grad school, like trying to contribute to open source projects that had any GPU stuff going on, like it was just really hard for me to get into. So are there like really good first issues on the GitHub right now that or will there be good first issues for people to tackle, maybe to like contribute to CUDA Quantum?
Yes, I'm not sure if they are right now, but
Sure.
we definitely want to add them. We love being an open source project, and we do look for contributions or suggestions or feature requests. And yeah, we want to participate even more in this type of events. So yeah, if anyone has any idea, please get in touch with us on GitHub or any other place. We did accept a couple of contributions before, and we're open for any ideas, and especially open source contributions as well. Yeah, we'll be really happy to hear from you.
Nice, cool. Another question I have is, so is there any interesting like quantum chemistry stuff in the works for CUDA Quantum in the near future with future releases?
Yeah, so we already have some support already.
Mm-hmm.
I showed it briefly in the VQE slide where we have support for building Hamiltonians and calculating expectation values and the VQE construct. We will have like more advanced tutorials around chemistry. We're also working with some kind of partners and customers in specific projects. We'll share them once they're ready. But the potential of performance improvements is really high here because of the specific type of calculations you have in chemistry applications, where you can really take advantage of multiple GPUs and multiple QPUs and the combination of them, right? So I showed this example of a Hamiltonian where you can, first of all, calculate the terms in parallel, but then for each QPU or emulated QPU, you can use multiple GPUs in order to scale the number of qubits that you support and the size of the memory. So you can find, it will take some experimentation, but you can find the sweet spot, right? If you have access to multiple GPUs, you can find the sweet spot between parallelization and scale and really be able to achieve significant performance improvements.
Right. Awesome. Okay. Well, we'll leave it there. Efrat, you'll be on the Discord as well, from what I understand. So people, if you do have any questions about CUDA Quantum, Discord's the place to be. We'll put the link to the Discord in the Twitch chat as well. Efrat, it was lovely to have you with us today. So glad we can learn more about CUDA Quantum, at least enough to get started. And lots of stuff from NVIDIA for the Open Hackathon, stuff to win. There's even a quantum computing internship and a research scientist position on our job board that you can check out. Thanks, Efrat, for joining us today. Have a great rest of your day, and hope you enjoy the rest of QHack.
Thank you.
Take care. Okay, everybody. That was really awesome. Again, go onto the Discord if you want to ask Efrat any questions. Next up, we have Laurent Prost from Alice and Bob. They're going to talk to us about cutting qubit counts with cat qubits. So stay tuned for that. We'll be back in about 10 minutes. Don't go anywhere. All right, everybody, we are back for another talk. We have Laurent joining us very shortly here. Just want a quick note, the Alice and Bob is sponsoring this year's QHack. So there's an Alice and Bob swag bag up for grabs and an interview with Alice and Bob for a position fitting their participants' profile and wishes. It's limited to 10 interviews and with priority for first prize winners. So definitely be participating in the open hackathon and you could possibly win that. Yeah, let's introduce Laurent. Thanks so much for joining us today. Laurent is a product manager at Alice and Bob with a background in applied math and 13 years of experience in product management. And he's leading Alice and Bob's efforts to make a quantum computer available on the cloud, develop a set of emulators, and much more. Laurent, very, very lovely to have you at QHack this year. How are you doing?
Hi, Isaac. Thank you for having me. Everybody's fine here. Greetings from Paris. It's 7:30 p.m. here. And I'll be happy to tell you tonight about cat qubits.
Awesome. Yeah, floor is yours.
Yep, thank you. Right. So I chose to name this presentation Cutting Qubit Counts with Cat Qubits because there is a topic in this hackathon where you will be asked to reduce the number of qubits. And this is precisely what cat qubits are good at. So I'm going to show you today how this works. Maybe a few words about Alice and Bob before we begin. Our purpose at Alice and Bob is to build a universal fault-tolerant quantum computer. We were founded 4 years ago by Theo and Raphael, who were PhD students working on cat qubits, and who decided to make this available to everyone by building a company. 4 years later, we've raised 30 million euros in VC capital. We've hired over 80 employees. And we've had a number of very interesting achievements that I will tell you about in the next few slides. But before we dive into the specifics of what we do at Alice and Bob and what we do with cat qubits, I would first like to tell you about logical qubits and the qubit overhead that they introduce, because this is basically what we're fighting with our approach. The first thing that you need to notice is that there are several types of speedups that you can get with quantum computers. And a lot of the algorithms that we're studying only bring a polynomial speedup. While this is great on paper, if we want to turn this into an actual speedup, into an algorithm that's actually going to run faster, we'll also need to take into account the time it takes to execute quantum operations. And unfortunately, quantum computers are actually slower than classical computers who have been optimized over the past 50 or 70 years. And if you look at this use case here, you can see that even though the quantum algorithm is reducing the number of steps, we're going from 10 to the -9 to less than 10 to the -5, because each step takes much longer to complete on the quantum computer, the computation eventually takes longer. And so we go from a few days of computation on the classical computer to several years on the quantum computer, in spite of the polynomial speedup that we're getting in the number of operations. So if we want to have a useful quantum computer, what we believe at Alice and Bob is that you can't just work with a polynomial speedup and you need to have a super polynomial or exponential speedup. But getting an exponential speedup is difficult because the few exponential algorithms that we know require very deep circuits. And if we take Shor's algorithm as an example, you can see that it requires big O of n qubits to run on an n-bit key and big O of n to the 3 circuit depth. So that's a lot of opportunities to get an error. And if you do the math as it is displayed on the slide, you realize that if you want to break a 2000-bit number, you need to have an error probability at the level of each operation that is lower than 10 to the -12. I guess you know that we are currently very far from this kind of fidelities. We're at best at 10 to the -3. And the concerning thing is that these error rates are not improving fast enough. You see here on the left that superconducting qubits have been improving over the past 20 years. We've gained something like 6 or 7 orders of magnitude over 20 years. And you can also see that even in other technologies, the progress is not as fast as we need it to be. If we wait for physical qubits that have 10 to the -12 fidelity, we're likely going to wait for it. So we need to have another solution. I trust most of you here are familiar with quantum error correction, and that enables you to build logical qubits. But there is a big problem with logical qubits because even though they enable you to reach the error rates that you need to run these big algorithms, they also come with a large overhead in terms of number of qubits. And so if you take, for example, a paper, the papers from Google where they explain how they implement quantum error correction on transmon qubits using a surface code, you can see that if you want to run a Schultz algorithm for RSA 2048, you need to have something like 6,000 logical qubits, and this translates into 20 million logical qubits, which is really a lot, especially if you look at the size of the current machines that we're able to build. Because we have this problem at Alice and Bob, we chose to go for a specific type of qubits, the cat qubits. And the good thing with cat qubits is that they are very well protected against one of the two types of errors that you get. So you have bit flips, so that when you change the 0 into a 1, and you have the phase flips, which is when you change a plus into a minus. So errors on different axes of the block sphere. And with cat qubits, you can tune them so that they have a lot fewer bit flips than traditional qubits. We can take the lifetimes from a few hundred microseconds to 10 seconds or even 100 seconds. You have the links to the papers below if you want to see how this is done. And this comes at an expense of shorter lifetime in terms of phase flips. But the shorter lifetime in terms of phase flip is not such a big deal because we can deal with the phase flips with a repetition code. And this is how it works. So if you take an approach that uses the surface code, if you want to repeat your information something like 30 times, you're going to need about 1,000 qubits in order to create just one logical qubit. Whereas if you use cat qubits, because you only have one type of error to correct, then the estimation goes down to something about 30 qubits in order to create a logical qubit. And we can do now even better using LDPC codes instead of repetition code. And if we look at the resource estimation that this gives us, then we go from 20 million physical qubits using a surface code to 350,000 cat qubits if we use a repetition code, and even 100,000 cat qubits if we use LDPC codes, as we show in our most recent papers. So you can see that this is a reduction in terms of number of qubits of up to 200 times compared to a surface code approach. And this is not just a theoretical achievement, it's also an experimental achievement. We've been able to show that with one cat qubit, you can achieve the bit flip lifetimes of about 49 transmons. If we compare with a Google paper. And the cat qubit approach has also been chosen by Amazon to launch their quantum computing initiative. And if we look at the blueprint that they published in 2020 or 2021, I'm not exactly sure, when they launched their initiative, you can find over 150 mentions of Alice and Bob's technology. So as you can see, cat qubits are very promising way to implement logical qubits. And we let you experiment with cat qubits using our software toolkit that's called Felis. And so Felis is supported by Qiskit. So it works as a Qiskit provider. It gives you a Qiskit backend on which you can execute your circuits. And it will let you soon access real hardware. So I'm just doing a bit of teasing here. So we're soon going to make a real cat qubit available for you to test and to witness all the figures that I gave earlier. So stay tuned for this. But for now, what you will be most interested in is the emulation capabilities of Felis, because we have two types of backends. We have physical backends that let you study error correction, and logical backends which let you run algorithms. I'm going to explain in a bit more detail what this means. So when you have a physical backend, then one qubit in your circuit is going to correspond to one qubit on your chip. This way you can reproduce what it looks like to work with the chips that we currently have, because we do not currently have logical qubits. So we're building what it takes to build one, but you will see what it takes to implement error correction on actual physical cat qubits, featuring the noise bias that I showed between bit flips and phase flips. And the problem is that if you use physical backends in order to run algorithms, then you will have to implement all the error correction mechanisms manually. And this is going to be way too much work. And this is also going to be way too hard for the emulator to run the number of qubits that you need. And this is why we developed a second type of backends, so the logical backends, in which we abstract away error correction. And we, in this case, the 1 qubit that will be in the quantum circuit that you define is going to correspond to several qubits on an actual chip with error correction running in the background. So when you use a logical backend, then you get a universal set of gates, unlike when you're running the physical backends. And then you can also tune some parameters to, for example, increase or decrease the code distance and see the impact of errors on the results of your code. And in both types of backends, then you can tune some parameters. So you can, for example, tune the number of photons in the cat qubit, which enable you to tune the bit tree phase trade-off. You can have then maybe a shorter bit tree lifetime, but it's going to give you a longer phase tree lifetime. So you can then this way find the best compromise for what you're doing. And you can also change the hypothesis on the hardware quality. So especially kappa 1 and kappa 2, which are the two main parameters for cat qubits. All of this is explained in more details in our documentation. So you can get Phyllis as an open source library. So the link is right here. You can just install it. You can install it through pip. You just type pip install Qiskit and Bob provider, and you're going to get Phyllis installed. You can also play with it on OVH Cloud, and this is in this case you get a pre-set up environment. You don't need to do the pip install and everything. So you need to go to the AI notebooks and set up a notebook using Phyllis. Just be aware if you do this that you'll need to update the version of Phyllis, because it's we've made recent updates on it to improve the compatibility with third-party libraries. And so this needs to be done manually in OVH Cloud for the moment. And we also have a PennyLane integration thanks to the students at ETS Montreal, who have developed an integration with PennyLane. So if you do anything with PennyLane, then you can use easily the backends that we do. And so just go and check out how they do it on their side. But Phyllis, for now, is not able to perform what we call resource estimation. So which is the work that I explained earlier, the work of explaining, so for a given logical circuit that you want to run, how many qubits are going to be needed, how much time is going to be needed, what kind of errors do you need. And so this is something that I encourage you to look at during the hackathon, to try and wonder when there is a circuit that you've designed and that is solving a problem, to wonder how many qubits are you going to need to actually implement it on real hardware. And for this, there is a resource estimator that has been made open source by Microsoft very recently. So it features different types of architectures, not cat qubits yet, but we hope that will soon be the case. And this is even something that you might want to look at if you want to make your submission interesting. And so the resource estimator is going to take some quantum circuit as an input and give you the resource estimations as a result. And if you want to see how we have been doing resource estimation on our end, if you want to reuse some of the theoretical ideas that we've done, then you can look at our papers. So in which we gave the 350,000 qubit estimation and the 100,000 qubit estimation. So you have the links. You have the links right here. I'm going to share, because that's a lot of links for you to follow. I'm going to share the presentation on my LinkedIn account afterwards, and possibly also on Discord if that's possible, so that you can have everything, and so it's easy for you to retrieve it. And yeah, so I hope that you will find it interesting to work with cat qubits during the hackathon. I hope that it will give you some interesting ideas to further reduce the number of qubits that you're using in your circuits. And so if you have any questions, if you want to get in touch with us, don't hesitate to join our Slack community, the Cat Tree. You have an invite link here. We are also made available as a QR code, and it's also going to be available in my latest LinkedIn post. And I will also be on the QHack Discord server, to answer any questions that you might have and help you with anything you might want to achieve with CAD qubits. Don't hesitate also to visit the Alice and Bob website to check out our job offers. We have many offers for either internships or full-time positions. So maybe there is something that will work for you. And we offer interviews for winners of the hackathon that will have used CAD qubits. So be sure to make some projects with the tools that I gave you if you want to get the opportunity to get an interview or a swap bag from Alice. Thank you everyone for your attention, and I'm ready to take questions if there are any.
All right, thank you, merci Laurent. That was really interesting. Thank you for that. We do have some questions. So we have a question from Kentucky Kirby. How will we be able to get hardware access?
Okay, so there will be a private beta that will be starting quite soon, and then it will be available publicly on a cloud platform, on a marketplace.
Okay.
So everyone will be able to access the hardware in exchange for a not so small fee, but we're going to try and make it easy for people to at least make a few experiments and try to experience what it's like to work with CAD qubits.
I'm sorry if you did say this too, but is there like simulation of noise, or is there like a simulator that is simulating your hardware pretty much exactly? Like, is there like noise simulators built in?
This is exactly what I call the emulators.
Right. Okay. Okay.
So yes, and of course it has built-in error simulation, built-in error models, and it's necessary if you're working with CAD qubits because the main property of CAD qubits is to have this kind of biased noise. So studying CAD qubits without noise just doesn't make sense.
Right. Right. Okay. So I do have a question actually for you personally. How did you get involved with Alice and Bob? What was the story there?
Okay. Well, it's a funny story because I almost didn't make it. And so there was a job offer on Slack community of product managers that I just found up because I found it interesting. I found it cool that we were working on quantum computers in France. And then so the guy who became my manager messaged me and saw that I reacted to his post and said, "Oh, are you interested?" And I said, "No, it's going to be way too much complicated for me. I mean, quantum physics, I know nothing about quantum physics." But he managed to convince me, and because I had a background in mathematics, he found that it was interesting that I would still be able to understand what happens in quantum computing because a lot of it is mathematics. And indeed, well, I found it really interesting to be able to put together what I had learned during my studies on mathematics and then what I had learned professionally as a product manager. And I'm really happy that I made the move because, yeah, this is a super interesting field.
Nice, cool, right on. We had another question from Kentucky Kirby in the Twitch chat. So I know that cat qubits are just like many other like bosonic codes, like GKP qubits and stuff. So their question was basically cat qubits versus GKP qubits. Who wins?
Okay. Well, there are two different approaches because the approach of GKP is to reduce the two types of errors at the same time. And so you're going to need something like a surface code when you're working with GKP codes. But it's all going to depend on the errors that you're going to achieve. I mean, if your error rates with GKP are low enough, then maybe your surface code is going to be small enough for the number of qubits to be interesting. Whereas on CAD qubits, we all bet on the noise bias. We bet everything on the noise bias. And so if we can get a noise bias that is strong enough and phase sweep lifetimes that are long enough, then we can also get an interesting reduction in the number of qubits. So basically, it's all going to boil down to what kind of performance we can reach with our bosonic codes. I think both approaches are valid. We chose to go for CAS, but we also respect what's happening on the GKP side.
Nice, cool. You did mention that the penny lane integration or support that was made possible by some help from folks at ETS.
Yes.
in Montreal. They were actually here last week at the in-person QHack portion. So just shout out to them, and they're also I think in the top 20 on the on the ranking for the coding challenges currently. So just a bit of a shout out there. That's really interesting. Good for you guys. I think we'll leave it there, Laurent. Thank you so much for joining us. Again, Laurent will be on the Discord, so I think you said you'd share some of your links or links to your presentation, stuff like that on the Discord. So go on to the Discord if you'd like to chat with Laurent further. But Laurent, for now, j'espère que vous avez un bonsoir.
Merci beaucoup. Thank you very much.
Bye.
See you. Good. See you.
Okay, everybody. Next up, we have. Let me see here. Sorry, I don't have the present. There we go. Right, Vadim. We have Vadim from IonQ. Excuse me. Excuse me. You probably noticed too that I've been muting the mic and coughing and like drinking some bubbly to try and clear my throat. So excuse me there. All right. So IonQ is going to talk to us about best practices on Harmony, Aria, and Forte. So definitely come back for that. That's going to be a long one. Really excited to have IonQ on board for this year's QHack. So that'll be in 10 minutes. Don't go anywhere. Make sure to ask your questions to Vadim. He'll be on the Discord as well after his talk. So everybody's on Discord today. Anyway, we'll be back in about 10 minutes. See you shortly. Okay, everybody, welcome back. Next up, we have Vadim from IonQ. So we'll welcome Vadim here right now. Vadim has a PhD and is a staff developer advocate at IonQ, research engineer, instructor, consultant, experience in development and optimization of highly parallel HPC applications like physical modeling, data science, statistical analysis of complex systems, and now quantum computing. He's fascinated about new technology and constantly learning and educating others about it. Perfect resume for a QHack talk. Vadim, welcome. It's lovely to have you again. Vadim, you were here last week at the in-person event.
Yeah.
You're here.
That was fun.
Yeah,
a lot of fun.
You're here with us virtually. So thank you again for being here. The floor is yours to talk about IonQ.
Thank you. Thank you, Isaac. So yeah, I have pretty loaded background, and if you're interested, kind of it's all started by just kind of working on my PhD physics by simulating physical processes. So by doing that, got exposed to high performance computing because like I need to optimize the code we were writing as close to the hardware as possible, right? And then kind of while trying to analyze all those protein complexes, decide, oh man, like it's really difficult to just look at that and label it, kind of manually label them. So decided to use a little bit of machine learning. And you can imagine it was more than 10, 12 years ago. Oh my God, I'm old. So anyway, I got exposed to basics of machine learning and kind of went from there. Was working as a consultant engineer for several years until I built enough expertise to write a whole book about parallel programming and code optimization. And then kind of, transitioned into that evangelist / developer advocate role when I was helping developers to learn more about how they can code more efficiently, right, or use the hardware more efficiently. And it seems like now I'm doing similar thing with quantum computing. So basically helping others to understand where they can find the most useful information about quantum computing, how they can use the hardware the most efficient way. And for those of you folks who don't know what IonQ is the company we're using trapped ions technology as our quantum computer implementation. So basically it's ytterbium ions, which kind of float on top of the chamber, and harmony, aria, forte. Actually, that was one of the questions I previously had. What are those? That's our different types of different generations of our quantum computers. Forte is being the latest one. So my plan for today is to basically talk a little bit more about the hardware, because I find this topic very fascinating, and a lot of people, when they gonna understand what is physically happening on the hardware level, it's easier for them to also understand the optimization techniques, right? Or basically how to use it the most efficient way. So I will talk a little bit about the physics of quantum computers, what's happening basically in your trapped ions, right? Chambers. We'll talk about native gates, what type of operations, how we actually engage with those ions floating in the high vacuum, very chilled, not kind of microkelvin chilled. Our temperature is around say 5 to 10 kelvins, but it's still pretty cold enough to prevent all other molecules, right, or atoms flying around and decohere the state of the ion. So that's why the fidelity of trap ions are pretty high. It's naturally quantum. So we'll talk about native gates. I will talk a little bit about debicing and sharpening after that. That's the techniques for error mitigation used in IonQ. And my whole talk, I'm planning to probably finish around it will take about 40-45 minutes, and I will have 5 to 10 minutes to answer the questions after that. So that's the plan. Before we actually jump into the talk itself, let me show you how easy it is to use quantum computers, specifically IonQ quantum computers. So right here, I have AWS, brackets, opens, right? Oops. I apologize for that. So you basically have devices already available, right? There are several of them. And some of them are actually in the maintenance mode right now, right? Some of them you actually going to need reservation, which can be done through Bracket Direct. So if you go here, and IonQ Forte will allow you to basically reserve the device for your research purposes. So if you take a look, there is this somewhat mystical phrase with error mitigation, right? And I mentioned previously that we have debicing and sharpening. That's what error mitigation is for IonQ devices. All right, so it's pretty easy to use them, right? And there are several examples even coming from the default notebooks. I believe if you just look at the documentation, it's available on Amazon Bracket. We publish kind of similar materials with Microsoft. So Azure Quantum have the examples where you can simply look at the practical usage of error mitigation, how to submit the job to our simulators or to our QPUs. By the way, access to the simulators are free. So also, let me actually go to the IonQ.com. That's kind of our main website where you can find a lot of useful information about our plans, about our technology. That's actually how the chamber itself looks like. It's actually pretty small. It's about kind of that big, and it simply kind of keeps the ions floating on top of the chip with changing electromagnetic fields and also constant field by which helps to kind of squeeze those ions together in one chain. And that's actually going to be pretty important when we entangle into qubits, but I'm going to get to that in a second. So we supporting all three major cloud providers at this point. So AWS, Microsoft Azure, as well as Google Cloud. Majority of the languages supported as well, including Penny Lane. So I will be talking about this in a few slides as well. If you want to learn a little bit more kind of with the practical examples, I would recommend to go to resources, go to Resource Center, and there will be a lot of documentation covering kind of how you can start, let's say, with Cirq, with Qiskit, Penny Lane as well. So that's basically probably going to be the most useful resource to go and find information and read more about how you can code for IonQ quantum computers. So now let's go back to my slides and talk about physics of quantum computers, because I find it very fascinating. So the whole device, the chamber itself, is pretty small, right? It's about kind of that big. But you need to provide a lot of optical system, stabilize the electrical circuits, because the way how we control where the lasers are directed, right? All of that is done with the acousto-optical deflectors, and like you need to be very, very precise what the potential difference you put on top of those. Well, basically, it's a kind of piezo element, but all of that requires quite a bit of real estate. But overall, what you got out of that is the chain of ions, which is sitting basically on top of that inside the chamber with a high vacuum, chilled down to, as I mentioned, temperature around like 5 to 10 kelvins, so that those ions can preserve their quantum state for almost like hours. Honestly, it's the fidelity of their state is pretty high, right? So that's the kind of beauty of the trapped ion technology. But well, I need probably to say what is bad about this technology as well. And if you kind of familiar with different implementations of qubits, the gates are pretty slow compared to superconducting implementations, right, or optical ones. Yeah, that's kind of the downside of having trapped ions. But there are also a lot of benefits, right? It's naturally quantum, it have very long coherence time, and so on and so forth. So that is kind of diagram which is supposed to represent the all-to-all connectivity available in the IonQ QPUs. And basically what it means that with one MS gate, with one gate operation, we can entangle pretty much any ions in the chain we have. That is kind of different and beneficial compared to, let's say, superconductive systems, where you need to have kind of physically co-allocated or kind of closely allocated qubits, right, to basically make them entangled, to share the quantum state. In our case, in this chain, we can address pretty much like any ion and make them entangle. So there is no need for swap operations to move the your qubits closer to the other one, right, and then probably move it somewhere else. And I find it pretty beneficial for our implementation. Now about the native gates, just to kind of give you more ideas what's actually happening on the physical level of the devices, usually native gates, it's very advanced topic. Not everyone needs to use it. I mean, you can use the standard gate set with your Hadamard, CNOTs, and you're gonna be fine. Native gates is usually gonna be needed for somebody who's developing compiler or working on error correction, error mitigation techniques, right? Because you need to go down and basically directly work with the hardware to basically get rid of this black boxiness of the compiler, because compiler, the one we have, is doing a lot of optimizations, a lot of even error mitigation techniques, right? It will basically change the way how the circuit is actually implemented on the low level. So you can think about native gates as, if we're comparing it to the classical computer, it's basically almost like using assembler instead of your I don't know, C#, right, or Python, which is completely high-level languages, right? So once again, native gates, it's not for everyone, but I still find this topic very interesting because it explains what's physically happening on the device, right? And everything happening when you submit your circuit on the high level, it goes through the compilation stage and optimization steps. So compiler is actually pretty smart. We have really amazing people working on the compiler team who's just doing all sort of heuristical optimizations and tricks to get the maximum out of the hardware based on your, I can probably call it high-level abstraction circuit, right? What compiler is doing also behind the scenes, if you enable error mitigation, it's this debicing and sharpening techniques, it will also create the symmetric variance of your circuit, which will be executed to, I guess the basic idea is to get rid of systematic error. So if you have, let's say, under rotation somewhere, right, but then you kind of flip-flop the circuit, for example, change the order of the qubits you're using, right? So your ions will be in a different order, but the circuit will produce the same result, but you might compensate for that under rotation. That's kind of the main idea behind the devising and sharpening. It's the aggregation techniques which helps you to get rid of the noise a bit. But we will get back to it. So basically, that's what's happening on the compiler side, right? Or you can kind of completely overstep and submit your native gates directly. Right, and then native gates, kind of when the circuit is analyzed, it's kind of this intermediate representation translates into pulse representation. So basically, how the radio frequency package looks like, which is going to be modulated on top of laser. So that's how we actually interact with the ions. And then you kind of run your circuit multiple times, right? As many shots you specified in your code, and simply aggregating the result. And based on the type of aggregation you've selected, right? Just your standard average or the sharpening technique, which you're going to be using plurality voting. It will give you slightly different results. But once again, give me just a couple of minutes. I will get to that topic. So that's the compilation process, right? And I specifically was mentioning those native gates. So on the previous, well, 2 slides ago, actually, I was showing this all-to-all connectivity diagram, right, which were just basically represented as a circle. That's not what's happening on the physical level. On physical level, we have this chain of ions, right, which basically hold in one place by changing electromagnetic field. I guess I will try to a little bit simplify and explain how that's actually happening. So imagine that with electromagnetic field, you're creating basically like a saddle potential, meaning that if you have the chain basically along, let's say, this axis, the potential is helping it to kind of push the ions to be in that direction, but they might actually slide down in the orthogonal or perpendicular direction. But if you change the electromagnetic field quick enough, your ions basically almost like sitting in this well, right, and not going anywhere. So that's what we use to keep ions in the same kind of chain in one location, but they still can probably move around one of the axes. So because of that, to kind of keep them all together, we'll also use constant electric field, and with a Coulomb force, we're simply pushing ions at the ends to squeeze the chain together, right? And those ions are pretty close to each other. So even on the image right here, I put the number, so 5 microns. That's the distance between the ions. But we have acousto-optical deflectors, which can take the regional laser beam. Basically, there is a splitter which splits it into 2 parts, and this AODs, so acousto-optical deflectors, they can target even individual ions. So for the 2-qubit operations for the MS gates, when we entangling 2 qubits, that's kind of what's happening physically on the low level in the QPUs, right? We taking one source of the lasers, we're splitting it, and then with acousto-optical deflectors, we kind of modulate the laser beams with radio frequencies. The profile of that package, the duration, as well as kind of initial phase, will control what exactly we're doing with the ions, kind of how we engage with them, right? And actually, we only have 3 physical gates implemented and 1 virtual. And I will get to it in a second. But yes, if we kind of doing 1 qubit operations, it means that we only need 1 laser and kind of point to a specific ion we targeting, right? So our 1 specific qubit, and do some manipulations there. And if you want to entangle 2 qubits, you just basically use the splitter and acousto-optical deflectors to address those ions you want specifically to entangle. So that's what's happening on the low level. I like this slide because it actually shows those operations, right? On the left side, we have single qubit rotations. And as I mentioned, 2 parameters we can control is basically the duration of how long is the package itself, right? Photonic package, or how long we engage with the ion, and that will change the amplitude of the rotation. And second thing, what we can control is basically phase, right? Where the phase is shifted, and that will define the direction of the axis. So it can be X or Y, and then rotation, kind of the longer the duration of the package, the more we're going to rotate it around, let's say, Rx or Ry. And for the RZ rotations, just because we kind of have those ions rotating naturally, we simply, I think I mentioned that we have like 3 physical gate implementations and 1 virtual. So RZ is virtual. The way how it's implemented, the compiler, when it's doing this intermediate representation, transcription, yeah, I guess I can use this word, it's simply counting how long do we need to wait between particular gates, and it can calculate how much our rotation around the axis happened. Right, so basically all those RZs, we're not even physically engaging with the trapped ions. We just simply wait a particular amount of time, and we just know by calculating how much the rotation actually happened. Right, so that's your rotations. RZ, RYs, and RZs. So it's all controlled by just basically how long you engage or interact with your ions, and what was the phase shift. For the 2 qubits, I find it very interesting. It's, remember, we kind of addressing the ions we want to engage, and what happened, the way how I visualize it to myself, or can I interpret to myself, we simply allowing those ions we interacting with almost like create a standing wave. I mean, like it's oversimplification on a lot of levels, but it helped me to kind of visualize what's happening there. And that's why we need those ions to be close another. And good interpretation I've heard also is that we pretty much like have a virtual qubit represented by these phononic modes. So when you have those kind of vibrations, and they actually have to be phased, is that even a word? We're kind of in counter phase. In this case, you can introduce additional parameter to the Hamiltonian, right? And kind of pretty much like pumping a little bit more energy with your laser beams into those ions, but like a frequency used specifically not to excite them, in which case they're going to release the photon, right? But it's actually in between the bands to provide kind of to engage with them, and engage with them in such a way that pretty much your ions start sharing the same quantum state. Once again, oversimplifying drastically, I apologize for that, but I'm trying to kind of explain how I visualize it in my mind when I'm talking about quantum quantum systems, but still trying to have more or less kind of classical visualization. So anyway, with 2 qubit gates, that's what's happening. We simply can addressing those ions, we put them into almost like creating, yes, this phononic mode, additional mode. If you prefer, if you want to read more, the first link right here, Molmer and Sorensen, or MS gate, that's what we actually implementing on the low level, and that's kind of the gates we physically have. If you prefer more tensor or matrix representation, that's kind of the operations for all 4 gates. And yes, I mentioned previously that RZ is virtual. And GPI 2, that's your single qubit gates, right? And depending, as I mentioned, phase change, it will simply change the orientation, or kind of define the axis around which we are doing the rotation. And the MS gate is your entanglement gate. So your classical full set of gates can be easily translated or expressed through those 4 gates. So that's the example of C0, which actually looks like like 4 single qubit gates and 1 2 qubit gates. entangled gates, MS gate. So if you want to learn more and kind of dig a little bit more in details, I definitely recommend to go to IonQ docs and look for getting started with native gates publication. There will be more explanation about those gates and what they actually do and more of that. So it is available through, well, I'd say majority of the popular quantum languages. So example of using Qiskit, how you can use Qiskit to program or express your circuit in native gates. You will just need Qiskit IonQ. Just import those GPI gate, GPI2 gate, and MS gate, and then you can simply gonna express your circuit explicitly with those gates. Same goes for circ, right? You can just get them from IonQ native gates. And ta-da, penny lane. So if you want to read more, just go to ionq.com, docs using native gates with penny lane. I believe you just need to install the library from the GitHub, and then GPI, GPI2, and MS gates will be available to you, so you can just use them even in penny lane if you want. All right, so that's what's happening on the low level, right? So that's how we use lasers to interact with ions. Ions, if you remember, is just positively charged particles. We use ytterbium. It's a pretty heavy element. The reason why we chose ytterbium specifically, because it is heavy, so it's easier to kind of keep it in one chain. Plus, ytterbium have 2 electrons on the outside orbital, so it is kind of easier just to take one of the electrons out by, for example, once again engaging with neutral atom first with ions. So we heating up the source of the ytterbium, right, with ions, and then they kind of get trapped into the electromagnetic field and populate the chain. All right, so that's kind of physics. Now let's talk about debicing and sharpening. And a little bit about debicing and sharpening. I showed you the Amazon bracket previously, right? And somewhat mystic message that those QPUs are with error mitigation support. So I wanted to kind of share a little bit more about what the error mitigation is, and that is specifically this debicing and sharpening techniques. A little bit of schematics. I hope I can explain what is debicing and sharpening using these diagrams. But if you want to read more, there is the whole archive paper written by our compiler programmers. They go into this technique, motivation behind it, and the implementation details in more details. So let's start with debicing. So what is debicing? What is that error mitigation technique? And if you are not super familiar with error mitigation versus error correction, we do not detect errors happening with the qubits, right? But we reducing the error accumulated during measurements or during during the execution of the circuit. And let me get into details kind of how that actually implemented. So when you submit your circuit, and for Amazon bracket, I believe you need to specify more than 2,500 shots for debicing to be enabled. And what our compiler will do when the job will be delivered to QPU through AWS, it will, during the completion stage, create 25 or about 25 different variants, symmetric variants of your circuit. What does it mean? It will be doing some manipulations. I mentioned it previously. It can just swap the qubits we're using. So qubits in our case is just the ions, right? Ions in the chain. It can actually move your circuit to kind of neighboring qubits, right? And if there's any kind of systematic error, right, with the state of the qubit, the whole idea of the symmetric variance, flipping, moving, we also modify the profile of this package itself, right? So how the radio frequency modulates the laser beam. So it can be probably just flipped completely. And if there's any under rotation and or over rotation, right, or some of those kind of systematic errors, the whole idea is that those symmetric variants will help you to compensate toward those errors because they simply going to cancel out. Kind of that's the very basic idea. So we're not checking for the errors, but we're using this technique to minimize them. That's why it's not error correction, it's error mitigation. All right. So that's what the left side of the image, those A's and B's, supposed to represent. So what we're doing, we're just basically looking at those different variants, right, using different qubits, and they then contribute to the answer. Second part is sharpening. Sharpening, it's the way how you look at the results. So if you just simply, so let's say we have results from different symmetric variants, right? And we observe different results. If you just can look at all the results given to you and just aggregate it, you will see those erroneous or errors, right, due to quantum noise, the results which were caused by this quantum noise. And it's pretty common, right? We are living in the in the noisy quantum computers era. So how we can fix it, instead of by aggregating full statistics, looking at absolutely all the results, what we can do, we can just simply, remember we have those like 25 more or less symmetric variants. So we can actually get results from those and only collect the results which going to be present the most. So the idea behind this statistics aggregation is that we're going to be using plurality voting. Plurality voting, if you're from US, you might be familiar. It's basically the most observed result is going to be counted as the correct result. You have to know one thing, though. This approach, so sharpening technique, is great. It helps you to actually get rid of these noisy contributions, right? And only amplify the correct result. But your problem have to have those kind of single or maybe just a few, but more or less actually probable answers. If your problem, let's say something like quantum chemistry problem, when you're trying to simply build the profile, right, because you're modifying your parameters just a little bit and trying to find extremum, which is minimum or maximum, depending how you define the problem, this technique will ruin your results, right? Because it will be amplifying some of your kind of pick some of the contributions, right? So you will not get this nice energy profile where you're going to be looking for the experiment. So once again, I need to amplify, or kind of I need to say you over and over again. Sharpening technique is only good for the problems where you have a single peak or maybe just a few multiple peaks. So let's say if you have what type of problem? Hidden shift problem, right? Or somewhere where you're just looking for factorization, right? In factorization, we might have just a couple of contributors, but majority of the rest is going to be just close to zero. and they are close to zero only because of the quantum noise. And if you just dump that noise, right, and amplify the correct results, that's where sharpening works the best. All right, so that's the whole idea behind debicing and sharpening, right? And it's overall called error mitigation. So in the archive publication, which I referenced previously, and actually will be linked here as well, there is the whole mathematical explanation why it works. And if we just look at principal component analysis, it actually demonstrates that errors are reduced significantly by using those techniques, using just toy samples, using 4-qubit circuits, right? But also bigger ones. So yeah, if you kind of want to read more, because this technique can be applied even for different quantum computers, just same goes to aggregation or sharpening, right? So yeah, using plurality or majority voting. In the white paper, it demonstrates that it actually works quite nicely. To enable it in Qiskit or Circ, it's basically those additional parameters you submit to your job, right? Enabling debicing and sharpening. You can actually have debicing enabled, but not sharpening. So remember this example I mentioned with the quantum chemistry? You can have debicing, and it will help with the results. You will see less noise overall, so your profile will be more smooth, right? But please don't enable sharpening there. So just put sharpening into false, right? Or just simply do not even specify it at all. So that's how you can use it in majority languages. I think I mentioned before that examples available on Amazon as well as Microsoft. So if you just look at the GitHub, let's say Amazon bracket examples, right, under the bracket features, error mitigation, if you just look for error mitigation, you will see examples of submitting your job. In this case, it's ARIA, actually one of our it's not the latest. Forte is the one available right now, the latest one. But with ARIA, you still have like 25 qubits you can use, and it's available for general public without even reservation of the whole machine. So, which is pretty nice. All right, so all right. Where we at right now? There, yes, this example I was showing on ARIA, it's just basically, yeah, it just demonstrates that you can have kind of debicing off, debicing on. It will improve the answer, but if you only looking for a sharp answer, then with sharpening, it helps sharpen it quite a bit. All right, so let's see how good. Whoa, I almost on time. Okay, 38 minutes, perfect. So I think I'm ready for questions. Once again, if you want to learn about GPU devices, you can directly go to IonQ. And under the cloud, well, you can register for free to get the access to the simulators, but also you can read more or kind of get more information about the backends by just going to the cloud, ionq.com site, right? And basically all the devices like Forte, how many algorithmic qubits available there, overall qubits, gates supported, right? Information about the fidelities, all is available on the portal itself, but also you can find this information on the website if you don't want to go through the registration. And basically here we have all the information about currently available devices to all the public, right? I mentioned Forte, ARIA 1, they usually something, and the Harmony, one of the previous generations. Also, if you want to play with the simulator, there's Ideal Simulator, which is available completely for free, but also we reproduced the behavior of ARIA and Harmony, and you can simulate, you can have basically noisy simulator. So if you can see if your algorithm will be performing nicely, even with real quantum noise, although you're going to be simulating it, right? You can try to use this noisy simulators to see how big your circuit can be or how wide, right? So you can play around with all the noisy simulators as well as QPUs as well, and that's how you basically can get familiar with the IonQ QPUs. All right, so questions. Let me quickly take a look at Twitch and YouTube to see if we have any questions.
Yeah, thanks, Vadim. I actually have the questions written down here, so I'll
Perfect.
ask you them here. Thanks for that. That was really interesting. I really appreciate your time. That was really interesting. Very thorough. Thanks.
Tried my best.
Okay, so we have a question from Broken Symmetries. This was earlier on in your presentation, I believe. Phase, sorry, let me go back to the interview. There we go. Phase is measured with respect to an origin. So when we say control the phase of a pulse, what is the frame of reference for that phase?
It's a pretty loaded question. So basically the frame of reference, during the, let me actually go to the slide. Maybe
Sure.
It's going to be easier. Here we go. So during the initial stage, when we're doing all the calibration of the devices, that's where the frame of reference actually coming from. So we start experimenting, right? And yes, you're absolutely right. When you just interacting with photonic beam, right, with the ion, any shift or any even vibration in the ion itself might produce the results which you're not expecting ideally, right? So we always kind of doing those calibrations where we simply producing kind of test interactions first, and then measuring the result of those interactions. And if we expect a particular one, we can then calibrate or adjust in this case, specifically kind of phase, right? And that's how we define the point of reference. So we kind of trying to adjust those parameters to get as close to the expected modification or expected interactions with the photons, if it makes sense.
All right. Well, Broken Symmetries, right back in the chat if that answer didn't satisfy you. We had a lot of questions about like the sharpening part. So there was like debiasing and sharpening. If you can go back to that slide, maybe that'd be useful. Yeah, we'll start here with Dentucky Kirby. This sounds like you're just tossing out the wrong answers, but I know it can't be that simple. So why is that wrong?
It is actually it is the right approach. We simply tossing out the wrong answers. Yes.
Okay.
It is what's actually happening.
Okay.
Yeah. So just because we have 25 or about that amount symmetric variance which contribute to the answer, so probabilistically the correct answer, if you expect to have only one bump, right, one correct answer, or maybe just a few of them, you will observe them more often than just quantum noise.
Okay.
You can probably do the calculations when this hypothesis is going to be broken, right? It depends kind of on how noisy your system is, but like, yeah, it's can be calculated. But the whole idea is exactly, you're absolutely right. The whole sharpening technique is getting rid of these error contributions due to the quantum noise, and only collect those where we expect to have the correct result, right? And we hope that it's going to be observed, or those results going to be generated by more symmetric variants compared to just those erroneous results.
Okay. Couple more questions on this.
Yep.
So Broken Symmetries has another question. Are these debiasing and sharpening techniques better suited for trapped ion devices, or would they work equally well in other devices and other hardware?
I think it can be applied to other devices as well. So if let's say you have superconducting implementation, or maybe even optical ones, right? Having those symmetric variants will help you to get rid of the systematic error. So I would say yes, those techniques. It will be slightly different physical implementation, right? And maybe there will be some nuances and specifics depending on the qubit implementation.
Right.
But the general idea can be applied to pretty much like any qubit implementation.
Okay.
Or physical, yeah. Yeah.
Okay, one more question about this sharpening stuff from Kepunto. Hey, is the QML field suitable for these sharpening techniques? So similar to be like, I don't know, maybe there's like some error in your model and like, or just noise in your model, and you could just, I don't know if it's applicable there. Somewhat unrelated, but also kind of adjacent.
Yes, I think. Well, QML. They're different implementations, right, and different problems in QML. So unfortunately, the question is too generic. I would say if you kind of expect that there will be only a particular classes,
right,
if it makes sense, right, then yes, sharpening can be still applied there. So once again, the whole classification, the whole criteria, if you can apply sharpening or not, is based on what answer you expect. If it's going to be just a couple of few answers, right, then yes, sharpening works perfectly, because like it will simply dump or get rid of this quantum noise and only amplify your correct answers or kind of expected answers. But if it's somewhat profile, so if you have a lot of classes, or once again, depending on the problem you're trying to solve, if it's just a conversion function, then probably no. Sharpening will ruin it, because it can messes up with statistics aggregation, if it makes sense.
Okay. Right. Okay. One question from Andresu Lead. Hi. How to make error mitigation with IonQ? Can the error mitigation that comes from Qiskit, like zero noise extrapolation, etc., from an estimator, be used with quantum computer for IonQ?
I think it can. I can probably follow up if it's something you're really interested for your research. I would recommend just to quickly go take a look at IonQ website, where just search for error mitigation. And if you will not find the answer, I can probably just follow up with you. Just email me at karpusenko@ionq.com. And I know exactly the person I need to ask this question who exactly know the answer. So yes, please, if it's something your research is depend on, follow up with me. I would gladly find you the correct answer.
Maybe a good question for the Discord. So Andres Lead, maybe if you want to hop on Discord after.
Yeah.
Great.
Perfect. I will be on Discord, by the way.
Right.
Yep.
Exactly. I guess maybe a fun one. I see your QHack shirt back there that you got last week.
Yeah.
You have some nice LED light strips everywhere. What's going on there? I know you've blurred your background, but
so, all right, I'm always telling this story. I think that's one of the reasons why I got a job at IonQ, because while I was going through the interview a year ago, a little bit more, I gradually start building this thing behind me.
Okay.
This padboard, and the main reason was I had very messy table with a couple of computers, tons of wires, and I thought I need to put them somewhere. And I thought, what can I do? And that was the obvious solution. Let's just put the padboard, and then like it started growing, and I'm like, it's ugly. How can I beautify it? Okay, LED strips. Yeah, that works.
Yeah.
And basically just say, let me just put a couple of those around. Like, it looks nice. And people always have the kind of questions. So what is this? Like, oh yeah, that's the thing I built myself. And my kids, I have 2 kids, 5-year-old and 2-year-old. They like to mess with it. And you can control it actually remotely. So a lot of fun. It's almost like a hobby project for me.
Yeah. Nice. Cool. Definitely love a good Zoom background that's authentic and not like a fake one. So congrats. Nice. All right, we're ending really just right on time, Vadim. So I really appreciate it. And again, anybody have any questions for Vadim? Go to the Discord. That's where it's happening. So go chat with Vadim there. Vadim, thank you so much for being a big part of QHack this year. Last week in the in-person stuff and virtually here today. Yeah, thank you so much. Enjoy the rest of your day, and we'll chat soon. Take care.
My pleasure, and thank you for amazing audience. You did a great event, and all the people I have a pleasure to talk with, like, mind blowing, amazing. I love the community.
Yeah,
awesome.
Thanks, Vadim. Cheers. Have a great day.
You too.
Okay, everybody, we have another talk coming up from AWS. So we have Jagadeesh Pusapadi coming. They're going to talk about getting started with Amazon Bracket. So stay tuned for that. That's going to come up in just about 10 minutes. So don't go anywhere. Maybe just grab a snack, come back. We'll be back right at 3 p.m. Eastern. Okay, everybody. I started a little early here, but I just wanted to make a quick announcement about the Open Hackathon. For those of you who are already doing it, great job. You're getting a head start on stuff. This tab wasn't working for a little bit. We fixed that a few hours ago. So you can go ahead on the dashboard, click on the Open Hackathon tab, and look at everything here. Should be pretty straightforward what's going on here. So make sure you read everything, even the power-up stuff, all that jazz. All of it's right here. Again, we're doing submissions directly to our website, not through like pull requests to our GitHub repository or something like that. So any project that you have, it can be a GitHub repository or something like that. Just submit it through here. That's really it. So you have 6 days and 2 hours left to submit your project. So best of luck with that. Okay, so our next talk is from AWS. We're joined by Jagadeesh. Jagadeesh is a principal solutions architect for Amazon based in the UK. He's a quantum technologies enthusiast. He's passionate about helping customers build innovative solutions on AWS Cloud by providing architectural guidance. He also guides them to explore the world of quantum computing using Amazon Braket, which you are here to talk to us about today. So Jagadeesh, how's it going?
Yeah, very good. Thank you. Thank you for the introduction, Isaac.
All right. So you're free. The floor is yours.
Oh, thank you very much. Hi all. Nice meeting you. Today, I'm going to talk about how you can use Braket for your hackathon. I'll start with running through the console. I don't have any slides to share. I'm just going to run through the console, and I have a couple of our colleagues, Peter and Sebastian, who are doing support on the chat as well on Twitch. So please ask any questions away on chat as well. For the hackathon, you would have received credits for using Braket service. If you don't have an AWS account already, you need to get one created. If you have, I'm going to show through how you can redeem your credits, how you can enable and set up Braket. You can follow along while I'm doing it, but this session is recorded as well, so you can do the similar setup after as well. So the first step is to redeem the credits once you have created your AWS account. So for that, so once you log in, for those who are new to AWS, I'm just going to run through the console itself. So it's fairly straightforward. If you go to the home page of the console, you get some recently visited tab, some of the applications if you have configured, and general dashboard. One key thing to notice is the regions. So AWS services are distributed across different regions, and you get to select which region you're going to work on. A Braket service is only available on few regions, so it's important to pay attention to that. So first, for redeeming credits, you click on your username after you've logged in and go to billing and cost management, or directly from the console, you can start in the services part, you can start typing billing here, and you can get to billing cost management directly as well. Once you are here, you click on credits. And click on redeem credits. So you type in the credit you have received, the promotion code, and the CAPTCHA security part, and then click on redeem credit. So as soon as that's done, you should have credits added to your score. So when mine is currently empty, so you'll see the credit here and the total amount. And as you keep using, you will have the total amount left visible here in the billing console. So the next step is to enable billing alerts, because especially if you're using credits, it's important to make sure you're not keeping an eye on it and you're not accidentally using up too much of it. So for that, you go into Preferences and enable alerts. For receiving billing alerts, you edit, and then you enable billing alerts. So if you're a new account, you have free tier as well. So if you can also select to receive alerts when you exceed any free tier limits. And for this is email address. You type in your email address and click on update. So that enables alerting for you. Next is to enable access to third-party QPUs that are available on Bracket. So once your account is set up and you have enabled billing alerts, you go into Services and look for Bracket. And go into Permissions and Settings as a first step and enable third-party devices. So this is an one-time activity on an account. So once it's done, it is enabled. So this basically allows access to third-party devices. So this is mainly to read through the terms here on how the third-party devices are used from Bracket, and then you click enable. And if you're planning to run some of the hybrid jobs, there are two steps to do here. One is service-linked role. Click on that create service-linked role button to click that. So this service-linked role is allowing Bracket to access your AWS resources on your behalf. It's basically storing your results, running programs in other services of AWS for running your quantum circuits. And there is a feature called hybrid jobs. We'll look at that in a bit. Here, there is another requirement to enable create a default role for running this hybrid jobs. So click on verify exit roles. Mine is already here, so it's showing which role is existing. If it doesn't exist, this button will be enabled. So click on the create default role button here. So basically, as soon as you log in, go into Bracket, click on permissions and settings, enable third-party devices, and create service link role and the default role. So these are the two initial steps to get you started on Bracket. Right, so let me walk through the Bracket console itself and what is available here, how you can navigate and use the Bracket service. So in dashboard, you have access to resources. There is a Bracket digital badge for certification, so you can go through the learning path and achieve that Bracket badge as well. Access to documentation and the algorithm libraries are here, and announcements and the devices and simulators. So we'll look at each of these separately. So let's start with devices. Bracket has multiple simulators and QPU hardware from different vendors available. So this is giving you a full list of all the devices and simulators you can use using Bracket service. The first three are simulators: state vector simulator, a tensor network simulator, and a density matrix simulator. And then different hardware providers. From IonQ, we have 4 different devices available. From Oxford Quantum Circuits, we have Lucy, and QEra have provided Aquila device and Rigetti's Aspen device. So OQC and Rigetti are superconducting devices. IonQ is a trapped ion device, and QEra is a neutral atom-based QPU, which is using Rydberg atoms. For all of these devices within Amazon, when you want to use, it's not just for these devices, across all of AWS resources, we have a unique identifier for a resource. It's called an ARN, Amazon resource name. If you click on any of the device ARN is available here for simulator. So this is the ARN you will specify when you're building a circuit or you want to submit a job to a simulator or to a QPU. For any of these devices, you can click a device and then look at different details. One is the details of the device itself, the availability window, which region it is. So that's the important part, where it is located, and pricing details. And also, you can also get the topology and the calibration details for each of the devices. So these are the device details. Next, Bracket provides a managed notebook service. So go into the notebook. So when you create a managed notebook here, Bracket creates a Jupyter notebook using one of the other services called SageMaker. But that's all hidden away from you. You can just click this create notebook instance, select a name, and then there are many types of instances that support this Jupyter notebook. So here for now, we'll go with standard, but if you have any specific requirements for running local algorithms, the classical part, you can go for GPU accelerated or high performance CPU ones as well, or you can custom, there are many types of instances available. You can choose the right one that is needed for your use case. So we'll go with standard here, and you can select the volume size. If you're doing it for the first time, I would recommend click on a create new role. What this does is it creates a role and then attaches that role to the notebook you're creating with all the permissions needed for running the Bracket jobs. And if you already have a role created, you can select from the list. So all these are different roles we have used in the past. So I'm going to go with create new role, and then the rest you can leave default. So this is just a summary, and then click launch. So this takes about 6 to 8 minutes, roughly, just over 5 minutes-ish. Once this is created, it will automatically open, but you can always go back to notebooks, and one I created earlier today. Once it's created, it'll become in service, and you'll have a URL to access the notebook instance. I have it here. So if you click on the link, it opens the notebook Jupyter Lab environment in a new window. Right. So this notebook instance has got all the Bracket SDK and the dependent libraries all pre-installed. And also it has a copy of 2 repositories from GitHub. One is Bracket examples, another is Bracket algorithms. Within Bracket, I'll just quickly show algorithms, and then I'll come back to Bracket examples, which will go a bit more deeper. So within the algorithms, there are a few textbooks for common algorithms, where you can, there are libraries that make, instead of starting from scratch, you can use these higher level libraries in your applications and directly from. There are examples of how you can use all these different algorithms, and you can use these in your applications directly. Okay, let's go into examples. So here we have many categories within the examples folder. getting started is a good place to get started. So I'll go through how the bracket algorithm is used. I think this is the QPU one. Yep. So if we look at the native bracket SDK and how to use that here. For the bracket SDK, we have a cost tracking as an enabler, which you can start the tracker when you start when you are starting the execution of a notebook. I'll also, after showing this part, I'll also show how you can set up billing alarms in a repository, or one of my colleagues, Nihir, has shared a CloudFormation template, which you can run to set up billing alarms. I'll cover that in a bit, and I'll share the link for this repository as well. So you enable the cost tracking as you start the executions. And within Bracket SDK, you have local simulators and also simulators that are managed in AWS Cloud, and also QP devices. So here we're just doing some standard imports and then importing circuits and devices from the Bracket SDK. So this example notebook walks through what devices are supported and what gate sets are supported in each of those devices. So this is just picked 3 different devices from 3 different providers for the gate-based programming. QEra is not gate-based, so it is a special different paradigm of programming, and there are examples separately for that folder. So these 3 devices, you can get all the gates that are supported directly from the SDK, and this is for everything that's supported in the SDK itself, and then the different gates that are supported by different devices. So we'll look at a simple build state circuit. So here we're adding a Hadamard and a CNOT. So the way you construct the circuit here is you instantiate the circuit instance and then start adding gates. So this is done in one line, but once you have a circuit, you can, so we'll run this part and show you the circuit. But then you can also, once you've added, you can append more, like for example, X. If I say 1, so that adds X gate to qubit number 1. So just run this and print and show you the difference. So now it has added an X gate to qubit 1. And you don't have to predefine the qubits. You can always add like, so hold on, sorry, I didn't run this. Sorry, excuse me. There you go. So that has run now, and you should see additional qubit added to the circuit. So you can build these circuits dynamically, and you can also define these subroutines and programmatically build your circuits as well. So the SDK is very flexible on how you build and parameterize your circuits. There are many examples which go into very, very much details. Go back to the standard build circuit, and then first run it on the local simulator. So for local simulator, you don't even need an AWS account. So you can download this from GitHub and run it locally on your, once you have an SDK installed, you can run it locally on your laptop as well. So here, once you define a device, the way to run the circuit is a device.run, and then within the brackets, you give which circuit to run. So the circuit name you defined earlier, and the number of shots. So that's the way to execute a circuit, and this triggers a task. Because it's a local simulator, you'll not see that in our console directly. So it just runs here locally, and then to get the results back from the run, you can from the task that creates a task. From the task, you create use the results subroutine to get the results. And from the results, you can get the measurement counts, and then As you can see, it's roughly 526 and 474, and you can plot these. To switch to QPU or a managed simulator, for example, the only way is straightforward. You specify the ARN we talked about from the console. You can also get that from the SDK. We'll look at that in a bit. So we are setting up a device. Currently, we'll just pick OQC as an example. OQC has got longer availability during this the QHack. So we suggest you can use OQC for gate-based and IonQ as well. So IonQ, there are multiple devices. And also QERA for cold atom-based problems. So when you define, instead of the local simulator to run on a device or a simulator, you define a variable and specify the ARN of the device itself. And after that, it's the same method. The only thing is, if you're running it on a QPU, the results, I would recommend keep them separate, because otherwise the task will kind of wait until the circuit is run and you get the results back. And that can vary depending on how busy the devices are and when they're available. So I'm going to submit this job here in OQC, and that task has been submitted. Same build circuit, and it has been submitted on OQC. It's currently offline, so it's not going to run now, but it'll be queued. So this is what I was talking about. So if you go into quantum tasks, you will see some tasks here when you submit the task, but it's not visible here because you're in the North Virginia region. So wherever you run the job from, even though the notebook is in North Virginia region, the task itself will only run on the region where the devices are. So OQC is in London, so you have to switch to London region to look at those tasks. So this is the task we just created, UTC 2021. So that's the task we have created. So if you go into the task, it will have the details of number of shots, which device it's going to be run on. And once it is actually completed, you'll also get the results linked directly here. So let's switch back to North Virginia. Right. So that's very high level of how you can create and run on a device. Let's maybe run the same circuit on a simulator. That's SV1, the state vector simulator on bracket service. So here we are defining a GHC circuit. It's a parameterized circuit where you can pass in the number of qubits you want to build in a circuit to the function. I'm going to jump into the simulator directly. Hold on, sorry about the scrolling. Okay, SV1. So you are going to use SV1 to submit the task. So SV1 is a state vector simulator. It's a managed simulator running on infrastructure within AWS. So you're defining the device as SV1, and here we are specifying the number of qubits and 15. So it's a GHC circuit which maximally entangles 15 qubits. And then it's the same thing. You run it on the device. So the device is SV1, and you run GHC and then 1,000 shots. And you get the results back, and the measurement counts from the results object, and then we can plot it and see the difference between all ones and zeros. Right, we have run now, so we have seen the results all zeros and ones. It is a state vector simulator, so there is no noise, so you get these perfect results. Obviously, you're not going to get this on QPUs. So now we have run this in the region, which is North Virginia. So now if you go and refresh this, you should see a task here. So this is the task we just ran, and you see the task details here. So and the results I was talking about. So you can click on this. It'll take you to the S3 bucket where all bracket results are stored, and you can analyze those results there as well. The next thing I want to talk about is hybrid jobs. So hybrid jobs is a fully managed orchestration of hybrid quantum classical algorithms, where it's combining classical cloud resources like EC2 compute, say the containers or other instance types, along with QPUs. So the tasks that are created using hybrid job, they have higher priority queuing over individual tasks. So this is mainly because if you're running an iterative process, you want to make sure you run it on the device when it is in the similar config. So when you submit a job, the device is kind of reserved for that duration until your tasks finish. So you get higher priority access to the device you're running. So mainly to avoid any fluctuations within the device. So for each QPU, there is a separate queue for hybrid jobs. And at a time, only one hybrid job can run on a particular device. So if you look at the device, you pick any device, there was the number of tasks is really high, actually, over 4,000. There's another two queues here. One is priority tasks, that's different, and then hybrid jobs queue depth. So this is currently, so this is what I was talking about. So when you run it using the same task using hybrid jobs, mainly for the iterative, you get better access to the QPU. So so what we are going to now look at an example is using penny lane. So penny lane and bracket SDKs are like they work together very well. So here we are going to use hybrid jobs and penny lane to run a hybrid job. And there are, we have recently announced a hybrid job decorator, which is used to make running your hybrid jobs much efficient, the penny lane jobs directly. So all you do here is, we'll come to the decorator in a bit. So let's start how you can run penny lane jobs in bracket. So you import your standard libraries. And currently we're going to initially start with the local qubit, which is the local simulator from bracket. In penny lane, you can define as bracket.local.qubit, and the number of qubits here, that's the number of wires. So you import it and you define the circuit using these decorator, qml.qnode, and the device, so which is your defined here. So this is a standard rotation, 2 gates, Rx rotation and RY rotation in with different parameters. And then we are measuring expectation value on the Z basis. So that's the circuit. And then, so this is a routine where we are defining a qubit rotation with number of steps and different step sizes. And this is standard penny lane way of doing. There's a lot of documentation on how you can use penny lane and how you can use with bracket. Quickly, I'm not going to go into all the details of how you configure this. I want to show how you can use hybrid jobs with penny lane in a bit. So this, so if you define the qubit rotation, we are running this using the local simulator. So it's now running quickly and showing you the number of iterations and different values. Now, if you want to run this as a hybrid job, all you do is you define your circuit and your program, and then you instantiate using this a decorator, a hybrid job. And so here you pass in the device name, and you can refer to the documentation on what syntax is supported for different devices. So here we're going to use local, the same device, and define that. Oops. Did it run? No, it didn't. Sorry. Yeah, that has run now. So now, when I run this, so when you add a decorator, so when you call this program, instead of returning these parameters, what the program returns is actually the job ARN. So what happens is this creates a hybrid job, and the job details are returned as output of this particular function. So I'll run this, and then we'll go into the job and look at the details. Right, it has run and it has created a new job. So now you can look at the state directly from the SDK here itself. It's currently in queued state. Now let's go into the console and look at hybrid jobs. So that's the job we just submitted. It's on local bracket default. That's what we did earlier. So if you click on the job, so every bracket job takes some time to instantiate, because it has to spin up a classical resource, basically a container. Bracket comes with 3 default container images, one for a base image with standard bracket SDK, one for penny lane with PyTorch, and one for penny lane with TensorFlow. But you can also bring your own container image. So you can, there are example notebooks to help you build your own image as well. And you can bring that along here. So there's also another advantage of using hybrid jobs is you can use embedded simulators as well. So there are easy to instances types which have GPU. So if you want to run a simulation, quantum circuit simulation that can use GPU, you can use these hybrid jobs as well. So you can run these in like multiple, if you want multiple GPUs in the same instance, or run parallel across multiple GPUs, you can use hybrid jobs. There are some examples, again, using penny lane and multiple GPUs on how you can use these within the examples repository. Right now it's running. So once it's running, you can look at the events here. So how long? So it starts up an instance, downloads the standard image, and then when it says downloading the data, this is the circuit you are submitting and the instructions where it has to run. That is getting downloaded as well, and then the execution starts. Once the execution starts, you can look at the logs in CloudWatch. CloudWatch is our monitoring service, which supports logging from multiple AWS services, but you can also write your own mechanism to write log data into CloudWatch. And one other feature of hybrid jobs is, it's already run and completed. So you can look at the logs in CloudWatch. So you click on that link, it opens CloudWatch. For each job you're running, it creates a log group, and there are direct links to go directly into the one that's specifically for the job we created. And so here you can, so these are the initial setup for the hybrid job itself, and you can look at different parameters, and you can use hyperparameters to pass on different variables and control your iteration. So here this is just a simple rotation we saw in different expectation values, and it's the 10 different iterations. So this is just a simple example, but you can have a long running job with like hundreds of iterations to go through. So as part of the submission, I kind of skipped this. There is a facility to do log metric. So what this does is it starts logging after every iteration, it's updating a CloudWatch metrics, which you can monitor directly from the console, this monitor tab. So it starts logging the metrics, so you can actually see how your function is converging or not directly in the console. And if you see it's already converged, or if you achieve the results you're looking for, you can terminate the job early to save costs. Or if you see that even after like 300 iterations, it's not converging, may have to tweak, you can cancel it as well. So another advantage of the hybrid jobs is you can look at the quantum tasks here if they are running on like managed simulators here. We are running on the local qubit, so it's basically running on the container locally, so it's not submitting a quantum task per se, so that's why you don't see this. Right, so that's hybrid jobs at a high level. And it's the same thing, the example goes through and uses the same library to change to a different queue, so you can specify a QPU as a device ARN and then pass the same thing to hybrid job. The rest of the program is pretty much the same. So all you need to specify here, the device ARN and the decorator. Those are the only two places you have to change, and then the rest will run as you have here. So that's all the demo I wanted to do. Any questions so far?
We did have quite a few questions, but
sorry.
No worries. We did have quite a few questions, but Peter and Sebastian pretty much answered all of them.
Okay.
So yeah. Sorry, keep going.
So there's one more thing I wanted to say. There is so we talked about billing, and we enable billing alerts, but if you want to configure when do you want alert, there is a URL here which I can share. So you can implement this particular, you can clone this repo, and there are this enable billing alert CloudFormation template. You can use that to enable billing alarm. Maybe I could quickly show that if there are no other questions. So you go into CloudFormations. I will share the link of the repo in the chat. And so if you go into CloudFormation, make sure you download this file here, enable billing alert. So you go into CloudFormation. The repository itself has the instruction on how you do it. So I'm just wanted to make sure you're following it through here. So this is the part which talks through how you enable it. So you create stack with new resource, upload the file itself. Sorry, no underscores allowed. So here we are saying after $50, send an alert to the email. So you can adjust this on when you want your alert to be sent, and then click next a couple of times. There are no other. So this creates a billing alert, and it will alert you whenever when you are reaching that threshold you have set. And once you have set the billing alert, so you need to log the billing. So we talked about the cost tracker when you are running on the notebooks. So we saw here at the beginning in the previous notebook when we looked at, and you need to use that and use this function in your notebook as part of your executions. That way you are tracking the bracket cost directly, and when you add this, then you will see alerts within your email when you reach a particular threshold. That's all I had from a demo perspective. I'm happy to take any other questions or anything else you want me to cover based on the chat.
Sure. I think correct me if I'm wrong, moderators and Peter and Sebastian in the chat, but I feel like everything got answered. Oh, here we have a question from Panos Const, actually. What's the advantage of using cloud-based simulators instead of doing things locally?
It all depends on how powerful local machine you have.
Exactly.
So my standard Mac, I can simulate up to maybe 24 qubits on a state vector simulator. After that, you run out of memory and all the power you need. In the cloud, the state vector simulator we have supports up to 34 qubits, and tensor network simulator, which supports up to 50 qubits. So you can simulate up to 50 qubits in a tensor network simulator. So that's, and you don't need to pay for a very heavy machine. So you're only paying for the amount of time the simulator is used. And that's the advantage of using simulators in the cloud.
Yeah, Panos Const, every high performance computing thing will pretty much be accessed through like a server or something like that. Yeah, so pretty much everything high performance HPC is cloud based to some degree. Another question from Ivor Lynn. Sorry, I don't know how to pronounce your username. Is there oh, sorry, I got to scroll up here. Is there a way to automatically stop all processes when you're out of credits?
There isn't an automated way.
Okay.
So that's why we are recommending use billing, because you specify a credit card when you create an account, and that you have to keep an eye on it. So that's why you create an alarm. There's also budgets you can set in the billing, which is additional way. So overall, so here the billing alert we talked about is specifically to bracket. If you go into the billing console, there's also something called budgets. You can set that as well. So if you go into budget and you can set a particular amount, again, you'll get an email only. So there isn't an automatic way of stopping you from not running it or stopping your resources when you reach a particular thing.
Right. Had a question from Andres Ulid. Sometimes doing calculations on a GPU can be expensive on the cloud. Yeah, there is actually a free tier for Bracket that includes an hour a month for free. So thank you, Sebastian, for putting that in the chat. Yeah, GPUs are in high demand, and still I think the supply chain and stuff makes them like scarce to some degree. So such is economics, I guess. But yeah, no, Bracket has 1 hour a month for free. So there's that at least. Yeah, no problem. Okay, so if we don't have any more questions, actually, Jagadeesh, I kind of wanted to ask you some questions personally. So we were chatting before this. You said that you'd been with AWS or Amazon for 6 years. What did you do before this role that you're in right now, or were you always in this role to some varying degree?
I have been a solution architect in AWS for the last 6 years. I've been supporting different customers. I'm based in the UK. I've been supporting different customers, and quantum computing is my hobby and passion. So that's why I'm doing this almost as a side job. My day job is supporting life sciences customers in UK.
Oh, nice. Okay.
And I'm part of the quantum team and helping customers in EMEA as well.
Right, cool. What's your background in? Is it physics or something adjacent?
I did I'm not a PhD holder. I did a physics degree, and I have interest in this quantum area. But my job-wise, my background has been infrastructure, both servers, networking, and storage. That was
interesting. Okay,
background.
Cool. I'm not a PhD holder either. I just have a master's. I say just have a master's. I'm very proud of it. But anyway, no, I'm not a PhD holder either. I just couldn't do it. Yeah, I think that's becoming less and less of a thing, honestly. Like, it used to be like PhD and that's it. PhD or bust. Now it's not quite that. So thank goodness for that.
I work with lots of PhD holders within the quantum team. So it's
oh yeah. Same with me. Actually, Guillermo in the chat here. Guillermo, I think you're starting a PhD, I think. But Guillermo works with me at Xanadu. He just has a bachelor's currently. I say just as well, like as if it's like something that it's like not as good or whatever, but totally is like very respectable, obviously, right? Cool. how did you get started in quantum computing? Like, what was your first foray into this field? Was it quantum computing specifically, probably just based on your background, or was it physics? What was it?
It was my interest started when I started learning about the quantum physics, but then I almost didn't do anything until I got into AWS, and when I learned that's when Qiskit was getting popular as well and more mainstream. So I started in Qiskit learning before Bracket was a thing. I was playing around with quantum in Qiskit and attended the summer schools, and that's about time when Bracket was getting started as well.
Right.
And I've been working with the Bracket team almost from the beginning on the sides and trying to contribute how much, whatever I can, mainly on the testing side and getting to know the Bracket SDK, running it, experimenting, and also running workshops for customers, and just playing around and learning in the process.
Do you remember what your first contribution to Bracket was?
I wrote contributed to some of the example notebooks.
Okay.
In the repository, and also to the algorithms library.
Okay.
So I wrote the Schultz part as part of the Burger. So my contribution was to the Schultz algorithm notebook.
Cool. Right on. All right. Well, I think we'll wrap it here. Again, thank you to Sebastian and to Peter for being in the chat, answering all the questions. And to Yudo says, thanks, Jagadeesh. Yeah, thank you, Jagadeesh, for joining us today. We do have another talk from AWS. I think it's Zia that's going to join us this afternoon for half an hour. Yeah, another great comment here. Great orientation to Amazon Bracket. Yeah, definitely. We do have a video as well on Amazon Bracket, specifically the hybrid jobs feature. I think Alvaro put that in the chat. Yeah, just scroll up a little bit, and you can click on that. We did a demo on like how to use hybrid jobs and stuff like that with PennyLane. So definitely go and check that out. Jagadeesh, it was a pleasure to have you on here. Thank you for spending your evening with us here. Hopefully you enjoy the rest of your Friday night. Have a great weekend. Thanks for participating in QHack, and yeah, have a great night.
Thank you, Isaac. Thank you for having me.
Cheers.
Cheers. Thank you. Bye.
All right, everybody. We have 2 more talks today. Let me actually just put the schedule up here. Actually, you know what? Half the schedule's done, so I might as well just go to QHack. Hold on here. Cool. Let's just go to QHack. Let's look at the streaming session schedule. The next 2 talks we have are from Rowen, from Q-Control. So we'll get to talk about Fire Opal, which will be cool. And then we have another talk from AWS. Zia Mohammad's going to join us to talk about PennyLane and Amazon Bracket. We did talk a little bit about that with Jagadeesh's talk, but we'll talk about it more at 4:30. Also worth noting here, if I go to the Open Hackathon part, Hackathon challenges. Here we go. So I already announced this, but I'll just do it again for clarity. This tab is now working. I think there were some bugs with the website due to traffic right when it launched, but circa several hours ago, the tab's now working. Everything's fine. We're all good. You can get started with your Open Hackathon project. We already handed out some of the power-ups too from the coding challenges for your Open Hackathon. Also, the coding challenges will be closing at 5 p.m. Eastern, the coding challenge competition. So right at 5 p.m. Eastern, this leaderboard will freeze. How many teams do we have that solved everything? Oh my goodness. 16 teams. Wow, Quantum ETS, you just got in there. Nice. 16 people. Wow. That's pretty impressive. Nice job. Nice job, everybody. That is actually very impressive. So you do have about an hour and 10 minutes left to still compete in the competition. The questions will still be open after the 5 p.m. closing time for the coding challenge competition, so you can still get the badges and all that stuff. Let's actually go down to the badges. There's lots of cool ones. Some of them you can't get anymore because some of them are time-based, but all these badges can go on your PennyLane profile, which is really fun. So yeah, collect all these badges that you can. Thanks to our lovely designer for making all these awesome badges. I think my favorite one is Never Gonna Give You Up. Made a correct submission after 50 incorrect submissions. We had a team that actually got that very quickly. So, and by very quickly, I mean very quickly. But anyway, yeah, have fun with this. You can still get the badges up until I think maybe a couple weeks after the competition. I'm not actually sure, but yeah, have fun with the competition still. There is an hour and 10 minutes left to climb the leaderboard. So have fun with that. I just want to actually say a quick shout out to our sponsors. Thank you to all of our sponsors. We've been hearing all the cool stuff that you're up to today, but thank you so much for all that you've done for QHack so far. I really do appreciate it. All right, so we have Rowen coming up at 4 o'clock here in about 10 minutes. We're going to talk about Fire Opal. So stay tuned. We will be back in 10 minutes. Okay, everybody, welcome back. We have two more talks. We have Rowen joining us shortly from Q-Control, and then we have Zia from AWS joining us at 4:30. But let's introduce Rowen. So Rowen is a product manager focused on building emerging technology and applying it to real-world applications, driven by a passion to usher in the next generation of quantum computing. Rowen is making quantum computers useful by delivering enterprise-grade quantum error-suppressing technologies as a product that requires no quantum expertise. Rowen, it's lovely to have you with us today. You're joining us from sunny Los Angeles, and I'm here in sad, gray Toronto currently. How are you doing today?
Doing great. Yeah. Thanks, Isaac.
All right, so you're going to talk to us about FireOpal, so the floor is yours to get started there.
Cool. Thanks so much. Yeah, I'm Rowen. I'm excited to talk to you guys today about how we at Q-Control are making quantum technology useful. So a bit of an introduction to Q-Control. We are a company that is defining the quantum infrastructure software field. And so similarly to how you use classical computers today, you don't really need to understand processors or circuits in order to run applications, in order to view this webinar. And so this is all thanks to companies like VMware, Citrix, these sort of infrastructure companies that work behind the scenes and provide software that virtualizes underlying hardware. Ultimately, this all enables some application development, and it enables people to actually get value from classical computers. Q-Control is doing the same thing for quantum computers by improving the experience for application developers to build on top of these platforms, and by increasing the usability as well as the performance of these underlying hardware devices. The main way that we do this is really by stabilizing the hardware and reducing the error on the device, or helping others to reduce this error. A bit about how we work in the field. We work with all sorts of different organizations and companies, governments, labs, universities around the world use Q-Control products. We have over 14,000 users of our products, and we've powered billions of jobs, actual quantum computing jobs on real hardware. And then we're really humbled by the recognition we've received since our inception in 2017. We've gotten a lot of recognition lately, especially, and it's been really cool to just see the industry and the broader tech industry at large respond to the work that we've been doing. And so we're really looking to help people across the entire quantum computing stack, and at all stages of the quantum development journey to get value from quantum computers. The main focus of the presentation today will be on the product called FireOpal, which is targeted to developers and end users. And it's an out-of-the-box solution that allows anyone to achieve meaningful results from quantum computers with no hardware expertise at all needed. I'll also mention that we do have an educational product called BlackOpal, and this is essentially kind of a Duolingo for quantum. It provides interactive lessons that allow you to go from basically zero knowledge of quantum to becoming an industry professional. In fact, we have testimonials from users who have actually gotten job offers in the quantum industry after going through the entire BlackOpal course. I'll also say that all of our products have free usage tiers, meaning that anyone can go ahead and try them. They can get a lot of value from them even without paying a single dollar. And that really makes things accessible for anyone who wants to get started. And so FireOpal. I mentioned that this is really a tool for people looking to build applications and achieve meaningful results from quantum computers. So the core problem that FireOpal addresses is the fact that quantum hardware has a pretty significant challenge to overcome. They're incredibly susceptible to error, or what people often generally call noise. On the right, this slide shows a simple Grover search algorithm, which is basically a way to find a needle in a haystack. The result above is what you would get if you're running an ideal simulator, a simulation of a quantum device, where the correct answer stands out very clearly and there's one single correct answer. On the bottom, you see the actual implementation and results when you're running typically on the bare infrastructure of a real quantum device. And you can see that the correct result is almost completely obscured from all of the noise on the device, and you can't tell it from any of the other results that came out. This challenge is faced by almost anyone who's run an algorithm on a real quantum computer, and it even gets worse as you start to scale. So with bigger problems and more qubits, more gates, you tend to get more error, and this can be a really disheartening and frustrating experience for people, especially when they're just getting started on these devices. And learning how to counter the specific types of error that can occur requires oftentimes a high level of hardware-specific knowledge and complex implementation that's oftentimes not even very reusable. And so FireOpal aims to solve this challenge by providing an out-of-the-box solution that allows you to run valuable quantum applications without experiencing all of this error noise. Using FireOpal means that you can automatically get rid of errors on the device and just get quality results right upon execution the first time. It's a super simple to use solution. You can simply install it as a Python package and execute your circuits or your application with a single command. And then best of all, you can also reduce compute costs and achieve immense savings of over 1,000 times by getting the right answer faster and using deterministic methods that require no overhead or expensive sampling. So you get the best results within the first run. To put this quantitatively, we have all of these results in our published technical manuscript linked below, and they're also always continuing to improve. Especially as devices get better, we're able to achieve even better results, especially as the scaling challenge becomes harder. So first of all, we're able to push the limits of the intrinsic hardware to enable you to run deeper circuits. That means that you're able to run more valuable and interesting use cases up to 10x deeper, meaning that these are much more interesting problems that are more reflective of a real world use case. In addition, there's really that factor of savings across both cost as well as time and implementation. By reducing errors before they occur, that means that you're getting the best results with this single execution workflow. And this is really in contrast to other methods, such as error mitigation, which you may have heard of. This error mitigation method typically requires a lot of overhead, where extra executions are needed in order for you to post-process and figure out where the errors occurred on the device. This is an extremely expensive process, and so FireOpal achieves great savings in order to by eliminating this expensive post-processing. And then most importantly, you're getting the right answer by removing errors. And so performance, ultimately the answers that you're getting, the accuracy of the results is improved by a factor of more than 1,000 times. So what FireOpal really includes is it's a package that offers interoperability and connection to multiple backends. FireOpal today supports 127 qubit backends on IBM, which means that for the sake of your QHack project, you can use FireOpal with IBM's open plan and take advantage of the 10 minutes that they offer of free QPU time. Other backends, we're constantly adding and working with these hardware manufacturers to add them as supported backends on FireOpal. The great thing about the error suppression methods behind FireOpal is that they're all hardware agnostic. And so we can adapt them to the specific hardware and adjust them accordingly. All of this is done behind the scenes. And so our core error suppression pipeline automatically optimizes any quantum circuit. And then lastly, I'll touch on our hardware optimized QAOA module, a solver that is able to deliver correct results with high probability by optimizing the entire execution of a full algorithm in just a single command. So I'll give a detailed look at what's under the hood. I'm not going to go into too much detail behind these methods, as they're all quite intricate, and I could probably talk about each of them for at least 30 minutes. So feel free to ask those questions in the chat. But I'll just say that basically this represents our full error suppression pipeline, and it's entirely automated into that single command that you're seeing at the bottom, the fireable.execute statement. With this single line of execution, you get everything from reducing the size of the circuit so that, fewer gates means fewer errors. You're optimizing the mapping of the circuit to the hardware, using AI-driven gate optimization techniques to really replace what is going on in the circuit with things that are going to be more efficient. And all of this, still achieves the same result as your original circuit implementation, but it just achieves it more efficiently using hardware-aware methods. And so error suppression is really able to make quantum computing both useful and practical. Quantum computing time is extremely valuable, and it's a very expensive resource. So when you're running a circuit, you can specify the number of shots that you need. And each of those corresponds to a single execution of the circuit on the device. And then since quantum computers give you a probabilistic answer, if you keep running the experiment and getting the same answer, you become more confident that the answer you're getting is right. When you're reducing errors on the device, it's more likely that you'll get the right answer and receive this consistently. And so you can conclude your experiment sooner and know that you've achieved satisfactory results. The difference in that amount of runtime can be hundreds to thousands of shots, which is a ton of time and money ultimately. The graph shown here is a 10-qubit QFT circuit, which we ran both with FireOpal as well as some of the default performance settings on the hardware. And you can see that FireOpal achieved 99% confidence in the right answer in just 30 shots, whereas the default implementation took over 170,000 shots. So lastly, I'll talk about the hardware-optimized solvers that FireOpal also offers. This allows you to run entire algorithms from only high-level problem inputs. You actually don't need any quantum computing knowledge to take advantage of these. For this one, the QAOA solver, you can simply define your problem as a graph or a cost function. And so QAOA is a hybrid quantum classical algorithm that takes advantage of both types of computing. And we built a noise-aware implementation that achieves results that are 1,000 times better than standard algorithm implementations. Typically, the standard methods for QAOA just don't work on real hardware because they're not tailored for the noise. And so by tailoring every single part of this implementation loop to real hardware noise, you're able to achieve much, much better results. I'll give you a quick example of how this equates to a real problem. So MaxCut is a problem that often shows up in the fields of machine learning, and it's essentially a mathematical optimization problem. The goal is to make a cut that maximizes the number of edges that you're cutting across within a graph. And so this problem is within the complexity class of NP-hard, meaning that there's no known efficient way to solve this in polynomial time on the computers that we have available, classical computers today. So using FireOpal's hardware-aware QAOA solver, we've shown that you can actually achieve an optimal cut, aka find the right answer that as many edges of the graph as possible at a scale that was previously unimaginable. Shown here is an 80-qubit problem with 80 vertices connected completely randomly. Finding a good solution to this problem is extremely hard, even classically. In fact, classical brute force algorithms are no better than a random distribution, and that's really what's shown here in the red. Similarly, if you were to execute QAOA using standard implementation on hardware, you'd also find out that your results basically come out as random. FireOpal moves all the results to the right, meaning that it's finding results that are more and more edges included in the solution. The greatest solution that FireOpal found here, with a cut value of 106, was actually the optimal solution. That's the correct answer. This type of problem is incredibly hard to solve in using the methods that are available today. And it really gets into the scale and the realm of problem types that push beyond what is generally possible on classical computers, meaning we're getting closer to that space that we're all trying to achieve of quantum advantage. This is where we start to unlock the real value and potential of quantum hardware. And so I encourage you to push the entire field further and develop your QHack project on real hardware using FireOpal. If you have any questions about the product, how to get started, feel free to message on Discord or email me. You can simply visit our website to get started and sign up for an account. I'll also just mention that if you are early in your quantum computing journey, we do have an educational product that I mentioned called Black Opal, and it's a great way to get started and build the foundations that you need to learn all things that can take you to actually implementing a circuit and then running it in FireOpal. Okay, with that, I will pass it back to you, Isaac.
All right. Okay. Thanks so much, Rowan. Really appreciate your talk there. That was really interesting. I saw, I'm leaving this information up here for people who want to write down the website and stuff like that for a bit. But anyway, so there was did I see a mobile app for Black Opal?
Mm-hmm.
Oh, that's really cool. Yeah. Okay, awesome. Yeah. I feel like there's like low-key, I mean, obviously nobody wants to program on a phone. I certainly don't, but like low-key, having everything on your, like, I just downloaded the GitHub mobile app and I'm very happy at the moment with doing that. So I think the more we can put on mobile, that'd be great. So cool.
Yeah, totally.
So
yeah,
like, just like super small stuff like that, really, like, you know, I like that.
Yeah, I love that. Yeah, makes it just much more accessible and, you know, practical for use in your daily life.
Exactly. Okay, I'm gonna get to questions from the chat. Is there an iPad app for Black Opal?
I think it works across iPad too.
Okay.
Yeah.
Okay, I'll have to check this out. This is cool. Okay, so we have some questions. One from Dentucky Kirby in the Twitch chat. Is there penny lane support?
So we don't offer generic penny lane support, but
Okay.
we accept CHASM as an input.
I see.
So
Okay.
you can export from penny lane to, or really any programming framework, to CHASM, standard format, and then execute it that way.
Cool. Okay. They have another question. So FireOpal acts as a layer on top of the hardware, like kind of like data post-processing, or is FireOpal turning knobs on the hardware kind of? I think I know.
It does a little bit of both. It's basically kind of pre-processing your circuit to optimize everything, to make it ready to go into the hardware. Then it is tweaking things during the hardware execution. And then we do a little bit of post-processing too, but it's all one shot, one fell swoop. So there's no real like overhead or things that you have to do after the run.
And can you access those like intermediary stages that like okay, so I submit some job through FireOpal to like IBM's quantum computer, you know, looks at my circuit and goes, huh, that's weird. Why'd you do that? I'm you know, trivializing, right? But like changes what my circuit is. Like, can you access what it did to change, and can you see the thing that actually got submitted?
Yeah, you can see it in the IBM IBM dashboard, but we don't offer like knobs essentially. FireOpal is kind of a one-stop solution. Yeah, similar to like how your operating system performs and whatnot. Our ideal is that nobody really even has to think about error on the device.
Right. Cool. All right. Kind of related to this as well, we have a question from Keb.Punto. Hey, is it possible to know the details of how it works behind the scenes, or is like any papers we can look at?
Yeah, we have a published manuscript that actually talks about the individual steps of this pipeline that I showed. And so I think that I can also send the link to the paper in the chat, but yeah, it essentially goes into greater detail about what is happening behind the scenes in all of these stages.
Awesome. Cool. Yeah, like you did say, you will be on the Discord. So good place to ask Rowen more questions there. We do have to actually call it. Rowen, it was a pleasure to meet you today and have you talk about Fire Opal. I'm going to try and see if I can get Black Opal on my iPad. That'll be fun. Great to chat with you today. Enjoy the rest of your day. You'll be on Discord, so people who want to ask questions to Rowen there, go head on over to the Discord. Thanks so much for joining us today, Rowen. Take care.
Cool. Thanks so much.
Cheers.
See you all on Discord.
Okay, we are entering the final stages of the day. By stages, I mean stage, because there is one more talk. We're going to be joined by Zia from AWS very shortly here. So we'll be back in about 10 minutes. Sit tight. We got one more to go here. We'll be back in about 10 minutes. Okay, everybody, it is the last talk of the day. We're going to put the cherry on top of day number 2 of the sponsor demos. Up next, we have Zia. Zia Mohammad is a senior product manager at Amazon Bracket, bringing his experiences from venture capital and AI to quantum computing. Zia holds degrees in electrical engineering and computational neuroscience. That's super interesting. From Ohio State. Go Buckeyes, even though I'm not a Buckeyes fan. Go Tigers, LSU all the way. Beyond his professional interests, Zia maintains a community garden, is involved in technical policy, and is perpetually on the quest for New York City's best dessert shop. So, everybody, please welcome our last talk of the day, Zia. How's it going?
It's going well. It's always important to find a nice, sweet ice cream shop at the end of the day. So maybe I'll hit one up after this.
That sounds like a good plan. I might do that too. All right, so you're here to talk to us about Penny Lane and Bracket. So the floor is yours.
Yeah, no, thanks for the introduction. Really appreciate it. Today we're actually going to be doing a demo. We've worked closely with Penny Lane on the Amazon Bracket side. And so in today's demo, I'm going to briefly go over Bracket, show you guys some of the service dashboard, how that experience looks, and then actually dive into 2 examples. The first one will be around hybrid jobs, which is our quantum classical compute runtime. And the other will be, if we have time, of VQE, the VQE algorithm, and showing how you guys can use Amazon Bracket and Penny Lane together. So just to level set, go over quickly, Amazon Bracket is an AWS service. It provides customers, developers, researchers, everyone access to different types of quantum computers. It's a fully managed AWS service, and you can see that we have different types of providers as well. We have ion trap machines, we have superconducting, as well as AHS or analog Hamiltonian. And it's pretty important in this early stage that we have access to different types of quantum computing devices because each of them has their own characteristics. So what I'm sharing right now on my screen is the Amazon Bracket dashboard. If you have an AWS account, or if you are in the process of creating an AWS account, when you go to the Bracket homepage, you'll see a dashboard, has a bunch of announcements. You can see the devices that we offer, when they're available, and then you can also get specific information about them. So this is an IonQ device. You're able to see the topology, as well as specific calibration information. But today we're here to talk to you about Penny Lane and how you can use it with Bracket. If you go to the Penny Lane website, you'll see that there's a bunch of demos. In the demo section, there's a specific area for devices and performance. And today we're going to be going over 2 demos. The first is around hybrid jobs, and the second is VQE. Within the past 6 months, we've actually worked on something pretty cool with Penny Lane. In the right-hand side, in addition to seeing contents, for select demos, you'll actually see a run on Amazon Bracket hardware button. And so with this one or the VQE one, when I go ahead and click on it, it brings me up to this pop-up. You can see that there's a custom Bracket Penny Lane plugin, but then we can also visit the GitHub or sign up for Amazon Bracket. The Amazon Bracket and Penny Lane plugin essentially translates Penny Lane code and makes it consumable by Bracket. It's fully open source. We welcome any contributions, and you can actually see us actively developing it. There's open issues for the community, as well as the source code for you guys to look at. Additionally, for each one of these demos that we have, when you click Visit Amazon Bracket GitHub, it'll take you to that specific example that you can play around with, run locally, or on Amazon Bracket. So let's go back to the first demo, getting started with Bracket hybrid jobs. Penny Lane does a great example of showing you what is hybrid jobs, how does it work, and then actually providing you that source code. But what if we want to take it a step further and actually run this on a quantum computer or on a quantum simulator? With Amazon Bracket, you're able to do that and go that extra step. When you go to our Bracket console and you click on notebooks, you can see that I've created some test notebooks. If you don't have any notebooks, you can go ahead and create a notebook. But since I already have one, I'll actually just go ahead and click on that. In a new tab, it opens up our Jupyter Lab IDE. Inside of this IDE, we've already pre-imported all of the Penny Lane libraries and these demos that you can access. So if I go back to this, you see I have this first one opened up right here. On the left-hand side, if you're coming to this from scratch, we have a file repository where you can see examples, you can see all of the penny lane examples we have, and getting started features as well. But for today's demo, we're going to focus on a hybrid job. And what is a hybrid job? For those familiar with quantum classical algorithms, we know that these variational algorithms do best when there's an element of quantum processing and classical processing. But at times it can be cumbersome to maintain these. And so Amazon Braket hybrid jobs is the runtime environment that we use to actually manage the orchestration of these type of variational programs. In this tutorial and in this demo, not only do we tell you what Braket hybrid jobs is, but with a single line of code, we can show you how to use a penny lane simulator to run a full-scale experiment on a quantum device. So I'm going to go ahead and get this running. While it's running in the background, I'll chat. Let me actually restart the kernel and run all cells. So we're starting from scratch. And the best part is, this is that exact example that you see on the penny lane demos page. But in our Braket notebook environment, we've actually gone ahead and taken it a step further. If I scroll to the top, I can see, hey, intro to Braket hybrid jobs, and then get started with penny lane. You notice that, all the standard Python imports for penny lane, importing the QML device, and we're going to actually build a basic circuit. 2 rotation gates, and we're going to be measuring the expectation values. So from Braket hybrid jobs, we're importing this, we're building the circuit out, and then we actually run the algorithm. But how do we run it as a hybrid job? We recently launched this thing called jobs decorators. Essentially, it's a Python decorator that allows you to take your hybrid job and put it in the form of a function or a Python decorator. I do all of my standard imports. I have my circuit here. And with this decorator at the top, I'm specifying the local device. I have something called local mode turned on as true right now. This is just for debuggability purposes. But if I remove it, I can actually run it in my notebook environment. When I enable it, I can actually go and see, hey, if there's any debug issues or if there's any issues that I have in my programming, I can actually go and, deep dive into those. I've already pre-ran this circuit. So you'll start seeing, because I have local mode enabled as true, it's logging in, it's actually installing Docker, doing all of that stuff. But I've actually gone ahead and completed this. Takes a couple minutes, maybe less than a minute to run, especially since I'm doing this on local mode. But one of the things that I notice is I can get the job results. I can view these job results in my notebook, or if I go to the Amazon Braket console, I can actually see, hey, I've ran these 2 just now. I can see the specific tasks that I've ran, as well as the hybrid job. When I click on that hybrid job, this is a qubit rotation example, I can actually view these results in a graphical interface as well. So I'm able to see any events, when did it start, when did it run. I'm able to look at any monitoring metrics to see the number of iterations we went through, the expectation values for each iteration. And then if I want to create any tags, I can do that as well. If I prefer to do it locally in my Jupyter notebook, I can get all of these results programmatically as well. But for those customers who want an option to actually go and see, the visual element, do some more debugging, see the source code, the number of steps, specific hyperparameters, save it to an S3 bucket, I'm able to do that as well. If I keep scrolling down, I can see those simulator results that I mentioned earlier in the console, the iteration number, and then the corresponding expectation values. The best part about this is I can also run it on a QPU directly. So when I go to the penny lane demos page, I see all of the code. I can see that I run it on a local simulator, but I want to take it that one further step. I want to actually run it on a QPU. And so here you specify the device ARN. So IonQ is one of our partners, and they provide us their ARIA device. I can actually go ahead, take that same code, and just change this Python decorator to say, hey, instead of running it locally, now I want it to point to this device arm. Once I do that, I'm actually able to go ahead and check, hey, where is it? Where in the queue does it stand? How long will it take? So if I go back to the console and I click on devices, it might have already ran. I can see that there's one job running in front of me. So let's see if it's actually ran or if it's in the queue. It seems like it's still running, but I'm able to actually go and see through the bracket console that, hey, my job is running. Getting that visual element sometimes helps reinforce that, hey, it actually submitted, it made it through. And so while we wait for this algorithm to complete and download the result, let's go ahead and look at the other example that I was talking about with the VQE. Again, on the Penny Lane demos page, there's a brief overview of VQE. Again, going through that point, I can look through this code. I can see, hey, what is a VQE? How do I use it? How does it work? But if I want to take it that further step, I can click on that run on Amazon bracket. I can view the source code in GitHub. And then I can also go to my notebook and actually run it. So if I go over to the file explorer, I click Penny Lane, and you'll see, actually, let me expand this. There's a bunch of examples here. If I click on the hydrogen molecule geometry one, it'll open it up in a new tab. And then I can actually run this as well. So it's going to start running, but let's walk through this and see how this actually works. So what are we trying to do in this example? We're trying to use VQE, an established variational quantum algorithm, to solve a chemistry problem. In this case, it seems like we're working with the hydrogen molecule and trying to simulate some certain characteristics about it. I can see that in my notebook environment, it's already started going through, it's pulling Penny Lane data sets, and we're defining an ansaz. When it comes time to measuring the total energy and the spin of it, I can write my code, again, pulling from that Penny Lane example, but we're using that Lightning qubit simulator here. Scrolling down, we can see that, hey, we've gotten a result. Now we're minimizing the energy, trying to get that optimization. And this goes to give us this result. So we can see how many steps, again, the energy. If I go back to my device console, I'm able to view in the hybrid jobs tab. So this one is running right now. I can see, hey, ran large VQE simulation. Let's go and look at the events. This is when it started. This is when it ended. I can monitor those results and see, hey, how many iterations did we do? So in that code, we set the number of iterations to 29. And here's the energy levels at each one. I can see any tasks associated with it, as well as define any custom tags. Again, for those of you who want to stay in the notebook, you can view all of this data here as well. Same graph that we saw, but how can we scale this up? How can we run it on, how can we run it on a classical instance to a larger instance? And so let's use this hybrid jobs function that we were talking about. Again, we have that Python decorator where we specify the Python, or the device, and then we set up an instance config. So this is using the power of AWS and any existing compute that we have and saying, hey, this is the device, this is the configuration, and let's go ahead and run that. You can see it's just a function that we've defined previously. Again, when I go through that, I'm able to see, oh, we've gotten an error. We won't do any live debugging, but you're able to see that, hey, this is the quantum job, and then these are the result times. The CPU times, the wall times, and then you can actually plot the results. This is how you know it's a live demo, the joys of any live demo, but ideally we would have the graph outputted here. We can change the number of shots as well. With any good variational algorithm, you want to be able to customize it, play around with it. And again, as this demo illustrates, you're able to do all of that in the scope of Amazon Bracket from the existing Penny Lane demo. I'll pause there. I think there was 15 minutes for demo and then about 5 minutes for Q&A. So happy to take any question and answer. And maybe by the end of the Q&A, this will have finished running. So.
Yeah, thanks, Zia. As with the other AWS talk today, your little AWS minions in the chat have answered everything. So, yeah. So if there is something more you want to talk about, floor is yours. Otherwise, I have some questions. But yeah, up to you.
I think yeah. Before we get into some of the questions
Sure.
you have, I think the two things that we really want to highlight. The first one is the ease of getting started. And when you go and see a bunch of demos, you always wonder like, hey, this is great. I can run it locally, but what would it look like on an actual quantum computer? How would I do that? And right now you'd have to download the code snippets. You'd have to go and find the source file, make sure it works, upload it to the cloud. And so we've simplified these steps for customers. We have it on a select number of demos right now, but we've started increasing that number. And allowing customers to directly run things on Amazon Braket kind of eases that user experience. The second thing that I wanted to point out was this hybrid jobs decorator. So being able to run a hybrid job has been simplified down essentially into that one line of code. So here we've set that hybrid job Python decorator, if you're familiar with that concept. We set any parameters here, like what is the device name? Are we using local mode? Are we not? And then just have your regular function, and you're able to rotate this out for different devices. Let's say I want to use a Rigetti device or a different device. IonQ has another machine called Harmony. I'm able to type that in, run that exact same experiment, and reproduce my results on different types of quantum computers and different types of topologies as well.
Cool. All right. Well, if there are any questions for Zia, please put them in the chat. Okay, we have a question from Panos Const. Are hybrid jobs equivalent with sessions in Qiskit?
Yeah, so a good way to think about hybrid jobs is, to what I was saying earlier, it's if you're trying to run a variational algorithm that needs some classical compute and some quantum compute, and you're worried, oh, hey, how do I do that orchestration? How does that work? Hybrid jobs does take care of that for you, similar to what you'd expect in your current experience. And not only can you do it programmatically through the Braket SDK, but you can also do it through our UI interface. So if you want to create a hybrid job, and let's say you don't want to mess around with notebooks, you can do this all through our UI. So you can say, hey, what is my hybrid job name?
Oh, that's cool.
I can actually upload my algorithm directly, or I can specify an S3 location. So if I'm already using AWS and I have all of my stuff there, I can just point to a single S3 location. I can choose what container I want. So we have existing containers that have TensorFlow, PyTorch, or I can bring my own container as well. I can specify the device. So we can see that we have, Rigetti device, Amazon Braket simulators, or embedded simulators. So this is where I would use, Penny Lane Lightning or maybe some NVIDIA simulators. I'm able to actually select, hey, what kind of classical compute do I want? Do I want standard? Do I want it to be compute optimized, GPU optimized? Set the number of gigabytes of RAM. I can even set stopping conditions. So let's say I'm not sure how long my, variational algorithm will take. I can say, hey, please stop it after this many seconds or this many hours. An additional thing you can do is checkpointing, and I'll get to that in a sec too. But you can set hyperparameters. So if you guys were paying close attention to my demo, we had set some hyperparameters as well in some of those workloads. But as I'm going through these iterations in these variational algorithms, I can actually save data at specific points. And I can point to an S3 bucket that says, hey, after 1 iteration or 10 iterations, please periodically save my data. And then I can also output that data configuration to a specific S3 bucket. So I know that's a little more information, but figured since we were on the topic, I would also show you this user-friendly UI to emulate.
That's really cool. I didn't actually know that was there. I made that video a while back about hybrid jobs and stuff. That link's probably still in the chat. You can scroll up. yeah, I kind of did it all like the manual way, like just actually writing all the code. I didn't know that
Like
this
programming
existed.
it, yeah.
Yeah, I didn't know that this existed. That's really cool. All right, Zia, we'll have to leave it there, but you will be in the Discord. So if people have any questions for Zia and the AWS team, feel free to head over there. Yeah, it was really great to have you today. Hopefully you're able to find some cool ice cream in New York. I'm sure there's a place. I'm sure you know a place. Always. All right, Zia, take care. Lovely to have you at QHack. Thanks for being our final talk today. Really appreciate it. Have a great rest of your day. Cheers.
Thanks. You too.
Cheers.
Bye.
Okay, everybody, that'll do it for the sponsor demo days here at QHack. Yesterday and today, we had a lot of great talks from our sponsors. Let's go to our sponsors. Thank you all for what you've done in QHack. You've made this event possible. We really appreciate everything that you've done. If anybody wants to go and check out these talks later at your own leisure, you can go onto our YouTube channel. We were streaming to our YouTube channel this entire time, as well as on Twitch. But everything stays up live on Twitch, live on YouTube forever, pretty much. So we don't need to like worry about, it getting deleted or whatever. So everything's on YouTube. Go watch back every session we did, dating back to last week on Thursday when QHack began. Have fun there. Worth just going to qhack.ai as well, just to show what's going on there. The coding challenges are about to close in 8 minutes. To the coding challenge competition, that is. So you have 8 more minutes to climb up the leaderboard. How many more teams do we have that have done all of the coding challenges? Let's see. I think last time we were at 16. Still at 16, which is still really impressive. And there's a lot of people at like the final question. So congrats to everybody who's done super well in the coding challenges. Congrats to everybody who just participated and felt like they accomplished something. Hopefully it was a fun experience for you and you really enjoyed it there. Worth going over to the schedule as well. Next week, we just have one thing because you all will be busy with the Open Hackathon, which opened today. We'll be closing up QHack, unfortunately, sad face, next Thursday at 5 p.m. Eastern. We're going to be doing the closing ceremony and doing some meme contest judging. So yes, there was a meme contest throughout the entire event. If you have a funny meme, feel free to share it on Twitter, tag us there. Yeah. So hold on one second here. Right. So thanks everybody for joining. Really do appreciate it. Again, next schedule is Thursday, February 22. We have the meme contest. One of my favorite parts of QHack. We do that all the time. I love it. It's going to be a hoot. Catalina, Elon, and myself will be there judging your lovely memes. It'll be a hoot. Do join us for that. I also want to say a big shout out, thank you to our moderators and our green room hosts. We have a big operation behind the scenes here. So I want to say thanks to Guillermo or Ket.he in the chat. Ben, you've been organizing all the Discord stuff. I couldn't find your picture on Slack, but there's a B for Ben. Thank you for all you did, Ben. Really appreciate it. The Discord's a huge success, so thanks for that. Ivana, you've done an incredible job with all the sponsors, helping set up the Discord and being a moderator, all that stuff. Thank you so much for all you did. Catalina, you did just as much with sponsors and everything, being in the chat stuff. Quantum Catalina in the chat. Thank you very much. And then we have Alvaro. Broken Symmetries in the chat. Thank you, Alvaro. You were a great help. Alvaro and Guillermo and I wrote a lot of the coding challenges as well, so hopefully you had fun with that. Yeah, we have a great team here, and thank you for all that you did. Okay, so we're gonna wrap up here, but it's been a pleasure. I really hope that you guys all enjoyed these live streams. It's been a long 2 days for me, so I'm happy to put a cherry on top of this, even though it's a little bittersweet. Again, next week we just have the meme competition judging, so that'll be a hoot. It'll be fun. So make sure you tune in for that. It'll be a lot of fun. With that, I've been Isaac. You've been wonderful. Thanks for joining us today. You could have been anywhere in the world, but you chose to be with us today, so I really do appreciate it. And with that, we'll see you on Thursday. Peace.